Yeah. A very good morning to one and all present here. I, Srinivasalu, Assistant Professor, Department of ECE and CET, extend my warm welcome to everyone present here to the first session of AICT ATAL sponsored Faculty Development Program on Machine Learning Applications on Image Processing. To start with a quote, never stop learning. Learning gives knowledge and wisdom that can drive us towards greater heights, both personal aspects and professional career. And in this pandemic, learning has itself discovered in new ways and given a lot of opportunities to each and every individual. On that note, we would like to thank AICT Training and Academy, ATAL, for accepting our application to conduct and approve a fund of around 93,000 in conducting the faculty development program. We also thank our Nagarjuna College management for their constant support and cooperation in the conduction of the event. I am delighted to welcome Dr. Nagesh KN, Professor, HOD, ECE, and convener of this program. We are always grateful for your motivational support and guidance, sir. We welcome you, sir.
Thank you, Mr. Srinivasan.
I welcome the program coordinator of this event, Dr. Rohit S., Associate Professor, Department of ECE. We are grateful for your constant guidance and support in conduction of this faculty development program, sir. We welcome you, sir.
Thank you, sir. Thank you.
I am delighted to welcome Mr. Harish V., Assistant Professor, Department of ECE, and other organizing committee members, coordinators, teaching and non-teaching fraternity of NCE. Last but not the least, I extend my sincere welcome to all the participants who have joined with us for this program. Once again, I welcome one and all to this first session. Thank you all. Now I would like to introduce our chief guest and today's renowned keynote speaker. On behalf of NGI management, principals, HDs, teaching and non-teaching staff, we welcome Dr. K. Suresh,
Thank you, sir.
for the session. Welcome you, sir.
Thank you.
Now let us have a look. Welcome, sir. Let us have a look into insights of Dr. K.V. Suresh. Dr. K.V. Suresh received engineering degree in electronics and communication engineering in the year 1990 and MTech in industrial electronics in the year 1990, both from the University of Mysore. From March 1990 to 1991, he served as a faculty in the development of electronics and communication engineering, Kalpataru Institute of Technology, TechTour. Since 1993, he is working as a faculty in the development of electronics and communication engineering, Siddhganga Institute of Technology. He completed his PhD in the Department of Electrical Engineering, Indian Institute of Technology, Madras in 2007. His research interests include signal processing, computer vision, and pattern recognition. Dr. K.V. Suresh published more SEI index journal papers. He has presented more than 20 papers in IEEE conference and around 17 papers in different national conferences. Under his guidance, 3 doctoral theses are awarded, and right now 3 research scholars are doing the research. He is also a reviewer of articles like IEEE Transactions on Information Forensics and Security, International Journal of Intelligent Systems, International Conference on Emerging Computations and Information Technology. He has delivered technical talks on different topics on image processing in different reputed institutes. As a principal investigator, he has received a sponsored project fund of around 2.7 lakhs from AICT funding agency. He is awarded with many honors and awards. He is currently working as a professor in the Department of ECE, Siddhganga Institute of Technology, Tumkur. Thank you, sir, for accepting our invitation and being a part as a keynote speaker for a session in this faculty development. Thank you, sir. Now I request, Now I request Dr. K.V. Suresh, sir, our keynote session speaker, to take over the session. Please, sir.
Okay. Thank you, sir. Thanks for your nice introduction. Before I start, I would like to thank uh, Dr. Nagesh, whom I just came to know that he was my student. Thanks to Nagesh. Thanks to Dr. Rohit, who has constantly interacted with me for making some arrangements. And special thanks to Mr. Mallanna, who was my ex-colleague at SIT and who is a faculty now with you, for in fact introducing me to Nagarjuna College. This is an opportunity, in fact, to interact, unfortunately, through online. Otherwise, I would have been very happy to be a part of this FDP offline. I have visited your campus, in fact, several times. When Dr. Haribut was a faculty there, I had visited Nagarjuna College campus. It's a very nice campus, a beautiful place. So I would be actually sharing my slides now, and I request any one of you to
Srinivas sir,
just.
please stop sharing. Srinivas sir?
Yes, sir. Yes, sir. I'll stop presenting. Yes,
Yes,
sir.
sir.
You
Now you
can
can.
present it.
So is my screen visible, sir?
Yes, sir. Now it is.
Okay.
Yes, sir. It's visible.
So since this is an online presentation, probably just to know whether I am audible, the slides are visible. I request any one of you to just keep interacting with me and let me know if there are any such technical issues.
Sure, sir.
So,
I'll coordinate
okay.
with you.
Oh, fine. So, thanks once again for giving me this opportunity. It's always nice to be a part of such FDPs because you'll come to know each other. As um, Mr. Srinivasulu has already introduced me, I work in the area of image processing, and this FTP being machine learning applications on image processing. It would be nice if the participants have a hold on the basics of image processing and also the various applications on which we can discuss. So that is why I have titled my talk as Image Processing and its Applications, a bird's eye view. Let us move on. So this presentation will have actually two parts. Initially, for the first probably about 40 to 45 minutes, I will be just introducing you to the basics of image processing, maybe some terminologies. Of course, those of you who are already into image processing and who are teaching or doing research in this area, this would be a repetition to you, but nevertheless, basics is always important. So I think we would definitely be happy to know these topics. The next part would be on applications. So here I would like to share some of the applications on which we have worked at SIT, maybe as a part of our UG students projects or PG projects or my PhD students research activity. Okay, so this would be the outline of my presentation. Let us start with some basics. Now, I think whenever you just open up any textbook on image processing, the first sentence that we see is this: vision is the most advanced of our senses. So people would like to see rather than just listening. So images are very important, and particularly for our perception, they play a single most important role. Now, on this slide, I hope all of you can see an image. Since if any of the participant can just comment about what is the information that this image is conveying, I would be happy. You can unmute if possible, and please let me know what is this image trying to convey. Any Any participant who would like to comment?
So frog and duck,
Yeah, correct. You are right. There is a frog, there is a duck, correct.
both of them for the survival of the fittest, they try their level best, sir.
Yes, so yeah, I think you used the right word, survival of the fittest. I'll put it in a different way here. What is
Yeah.
happening is this frog is being almost swallowed by the duck, but the frog is holding the in fact neck here such that the duck will not swallow it. That means it is trying its best. It almost it is sure that it is going to die, but it has not given up. It is still trying to try its best till the end, so that it is still not going inside. So, in fact, this is a message that says never give up. In fact, many times, particularly when we are pursuing research, I personally have seen this type of scenario. Uh, uh, like there would be a situation when you are almost giving up, but you are not supposed to. So what I just want to convey here is an image like this, even though I have not typed any text on this, it has already conveyed so much of information. So when that is the case, processing such data for further, in fact, understanding would be important. Now, I think these are some basics. All of you know that an image is a two-dimensional digital signal. So it has X and Y coordinate. F is the actual gray level value at X and Y. Now, if f, x, and y, they are all discrete and finite, we call such an image as digital image. For example, if you look at this image, this is a very famous image called Lena, which is extensively used in research work. And in fact, most of the researchers will apply in their algorithm on Lena image first, and they just show these results. What I'm just trying to show here is a small portion of the eye is shown here. You can probably observe the pixels here, and the respective values are shown here. For example, this is something like 76, 46, and this is 116, 137. That means each of this will tell me about the brightness. So for example, in this region, the values are around 200, whereas in this region the value is less because it is 40, it looks dark. So each of this we call it as a pixel, which is the smallest unit of a digital image, and a matrix of pixels is actually a digital image. So if I can perform some operations on this matrix, I know how to perform digital image processing. So processing digital images using a computer is called digital image processing. So uh, in fact, after the advent of computer from 1960, a lot of such digital image processing has happened, and there is a huge, in fact, growth in this area. You will see through applications in the later slides. Okay, so the next definition that we would like to know is what is known as brightness resolution. When I'm representing an image by using some number of bits, the number of bits that I use to represent each gray level decides about the brightness resolution. So as you can observe here, here you only have two brightness levels. You have a dark level, you have a bright level. Whereas here you have used more brightness levels. I hope you can observe some shades. For example, there is a dark shade, there is a lighter shade here, there is a still lighter stage here. So as you can see, as the number of uh, pixels used to, sorry, the number of bits used to represent an image increases, you can see the representation of the image also improves. So number of bits decides about the brightness, and usually the standard is 8 bits is the representation. But in cases of medical images, we even go up to 10 bits and sometimes 12 bits. The next definition is spatial resolution. I think this is almost a known thing to all of you. The number of pixels that I use to represent an image is called a spatial resolution. You can observe here the number of pixels used to represent an image is less in this. So you could see some effect which we call it as checkerboard effect. Okay. See, whenever we need to do image processing, we have basic operations that are performed, and these are the very basic operations which we need to. These are some pre-processing steps that we may have to do whenever we are performing any image processing application. First of them is translation, scaling, rotation, warping, and then of course interpolation and resampling. I may not go into the details of the mathematics here, but I think with quick look at the equations, you can understand. What I mean by translation here is shifting of an image. See here, X and Y are the coordinates, A and B are the constants. So when there is a shift in the coordinates from X comma Y to X plus A, Y plus B, I call this operation as translation. So you can observe the second image, which is a translated version of the first image. I can also perform rotation, of course, with an angle of rotation theta. So the new coordinates x dash and y dash are calculated by using this equations. So you can observe here this image is rotated by a small angle. Now, where do I need these type of operations? Let me just show you a very good example. All of you should be knowing about this leaning tower of Pisa. This tower has actually, because of some poor foundation, it has shifted to its right by an angle. So what I have done is actually I have taken this image and I have slightly rotated it to the left by a small angle and I have made it straight. So whenever you want to do such corrections, for example, when somebody is working on fingerprint authentication system, the person would have slightly given a rotated fingerprint image and you want to make it straight by an angle, I can just use this simple operation of rotation to do it. So the new pixels are calculated based on the angle with which, so in fact, in this case, the angle is about, I think around 6 degrees is the rotation that I have done to the left. So the image has become straight here. So whenever I'm planning to do some corrections with respect to the images, we can do these translation and rotation. The next one is scaling. All of you know that when I just take a camera and you just move the camera in the Z direction, that means I just move towards the scene or go away from the scene, scaling happens. So the scale effect is, in fact, it is calculated by these constants A and B. So the new coordinates X prime and Y prime will be depending on the current coordinates X and Y and the scale factor A and B. Of course, there are other complicated basic operations like warping. You can just observe that there is a shear. You can have the complex rotation that has happened here. This is a scaled version. This is a warped version. And it is represented by a cubical equation here. So a nonlinear operation.
இங்கே போடு இந்த பால்கனில டைனிங் பால்கனில போடு அங்க ஒரு 3 துணி இருக்காது.
Participants are requested to.
Okay, thank you. So whenever I do these type of transformations, that means I just want to, for example, let us take X and Y as say 2 and 2. And if the scale factor is say some 0.9. So 0.9 into 2 is 1.8. So 1.8 is the new location and 1.8 is not an integer value. Your image has to be a digital image. So I will not be having these new values at decimal points. I only have it at integers. So when I want to calculate these new values, which are not exactly falling on the integer positions, then I need to use a technique called interpolation. So There are different types of interpolations. The basic one is nearest neighbor interpolation, where you just copy the nearest neighbor pixel value to the new value. For example, if the value is 1.8 and 1.8 here, you just round it after 2 and 2. So whatever that lies at 2, 2 will be copied as a new pixel. So that is how I can do nearest neighborhood interpolation. And of course, nearest neighborhood interpolation introduces an effect called checkerboard effect. To overcome that, we use a bilinear interpolation, which is slightly better, which uses an average. That means it's actually an average of all the values, and it's actually a scaled value. So you will have a smoothing effect. For example, observe here, Lena image is rotated by a small angle. In the first case, we are using nearest neighbor interpolation, whereas in the second case, we are using bilinear interpolation. I am very sure that you would be noticing a checkerboard effect in the first image. You can see particularly at the edges here. And that is because since you are just copying the nearby value, both the neighbors will have the same pixel positions. That is why you see this type of effect. Whereas since this is almost an averaging, it is smoothened and compared to this. So bilinear interpolation is always better compared to nearest neighborhood. Of course, there are other operations like bicubic spline, which would be still giving you a better result. Now, another requirement in my basic image processing is, I think all of us have done this without really knowing what is happening inside. Whenever the image that you have downloaded it is of smaller size, I know all of you have zoomed it to the bigger size. Or if the image size is very large and it is not fitting the computer screen, we have scaled it down. So this operation is called downsampling and upsampling. Downsampling is the operation where you are going to reduce the size of the image. Upsampling an operation where you are going to increase the size of the image. For example, in this case, a 4x4 image is downsampled to 2x2. In this case, a 2x2 image is upsampled to 4x4. Now notice here, what we have done here is, if I want to convert a 4x4 to 2x2, we are taking alternate pixels here. See, A1 is copied, A3 is copied, A2 and A4 has dropped off, A9 and A11 are copied, the others are dropped off. This is one simple way of doing downsampling. Second way of doing it is you just average these 4 pixels. Hello? Okay.
Yes, sir, you are audible.
Okay. Yeah, I got some background disturbance. Okay, I think so. You can average this and write it here instead of just taking alternate samples. I can do an averaging. So here again, when you are upsampling, one simplest way of upsampling is you just copy this B1 as it is to all the 4 pixels. Similarly, B2. This is one simple way of upsampling an image. Okay. All of us have used Fourier transform tools for taking a signal from one domain to the other domain. So we also have 2-dimensional Fourier tools. As you can see here, you will have 2 summations as usual because the image is a 2-dimensional signal. So you will have 2 frequency parameters K and L. So when I take the Fourier transform of an image like this, I need to plot it as a spectrum. So you can plot it as an image. Now notice here the pixel values or the gray values are very small. That is why you don't see much. So there is a simple operation to improve this by taking what is known as logarithmic transformation. We would probably see this in the next slides to come. And what I show here, what I'm showing here is the magnitude spectrum of this image. And what you see here is the phase spectrum of the image. Now, what you should understand from the Fourier domain representation of an image is, see the center here, the origin here is the DC value or the average value. And you know the DC value of an image will be very high. That is why it is looking white. And if you just move along the x direction and move along the y direction, the white region is dominating. I hope you can notice it in your screen also. Now, what this indicates me is, in the original image, if I am moving along the y direction, if I am moving along the x direction, there is a lot of frequency variation that is happening. Obviously, see, if I start moving from this side to this end, you could see that the pixel values at this position are going down, increasing. That means there is a high frequency variation along this direction. Also, when I move along this direction, definitely you would see. So a spectrum like this will tell me along which direction the frequency is changing maximum. Now, you also notice here your phase spectrum is in fact is actually allowing you to show a lot of information here. Okay, so the pixel values are too much changing, which also tells us that in any image, the phase of the image carries maximum information. That is why the pixels are changing so much. Okay, so you could see this in the phase image. Now, to demonstrate, I don't know whether this is clearly visible on your screens. I don't know. Do you notice two dots here, one dot here and one white dot here? I don't know, because if you are watching it on your mobile phone.
Yes, sir. It is
Yes.
visible, sir.
Okay,
Yes,
fine.
sir.
Okay, so what this is conveying is, see, if I move along this direction, what is observed is the pixel values are decreasing from white to black and again increasing. That means this is giving you a type of sinusoidal variation. Decreases and then increases, again decreases and then increases. So, you know, when you take Fourier transform of sinusoidal signal, Fourier transform of sinusoidal signal, all of you know, it is two delta functions, one at the negative frequency and other at the positive frequency. A delta function in two dimension, you know that it will be two white dots, because a unit delta function means it has highest value. So that is why you see one white dot here and one white dot here, and this white dot is the DC value. So I'll see two impulses along this direction, because the sinusoidal signal is varying along this direction. Now, if you observe this image, along the diagonal direction, the sinusoidal signal variation is there. So I hope you can see two dots in the diagonal direction here. So this is to more understand what a Fourier transform of an image conveys. Now, as I told you in the last slide, phase of an image, that means when I take 2D DFT, sorry, when I take 2D Fourier transform of an image, the phase is going to convey a lot of information. Just to convey this information, a simple experiment is done here. We call it as phase dominance. What is done is, we have taken two images. Image one is a well-known Lena image.
You are not audible, sir.
Sir, we are unable to hear you, sir.
Your voice is not audible. Yeah, participants, please wait. Maybe there is an internet connectivity issue. Sir will join us. Dear participants, regret you. Sir has rejoined, so we'll restart the session. Sir, you can take hold. Sir, can you please unmute, sir? Your voice is not audible.
Okay. Is my screen visible, sir?
Not yet, sir. No. Yes, it is presenting now.
Okay.
It's
So,
visible now.
okay. Sorry for
Yes.
that connectivity issue. We will just move on. So I was talking about some of the properties of two-dimensional Fourier transform. One of the important properties is image translation. You know, those of you who are into signal processing, if there is a shift in the time domain, the corresponding spectrum in the frequency domain multiplies with an exponent like this. Now, I just want you to know where it is being used. Suppose if you are asked to find maybe the shift in an image, how much is the translation that has taken place from one image to the other image, we usually use this image translation. Because, you know, whenever I take Fourier transform of a shifted image, the magnitude spectrum remains same, whereas there is only the change in the phase, and that change in the phase is proportional to the shift that is m0 and n0. So I can use this information and obtain how much is the shift in the image. So I can use this image translation property to find how much is the shift from one image to other image. Similarly, if I rotate an image, the corresponding spectrum also gets rotated by the same angle. So you can just observe here, this is a text image and its corresponding spectrum. I hope you can see a dominating white line here. Do you see a white line here in this spectrum?
Yes, sir.
Okay. So what this indicates, as I already told you, is when I move along this direction in the original image, there is a maximum frequency variation because the text is going to change from, I see you have text here and you have white background here, again text, white background. So along this direction, you have maximum frequency variation. That is why this is dominating as compared to other angles. Now, when I rotate this by an angle, now notice here, this dominating white line is along this line. That is because I have rotated the image by an angle. Not only that, since I have rotated it, there will also be some variations along this direction, which you could notice here. So a rotation of an image, the corresponding spectrum also gets rotated by the same angle. This is one property which you don't see in one-dimensional image processing. And in fact, this property could be used to find text in an image. If I want to find text in an image, I can probably find the Fourier transform of that and just see in which direction there is a maximum variation in the frequency. So, you know, whenever there is a text, you will have maximum variation in that particular angle. So that would give me the text information in an image. Now, some of the pre-processing steps that we perform whenever we do image processing is image enhancement, where we do what is known as contrast stretching, spatial filtering, we do some edge crispening, and of course, we use some Fourier domain-based filtering also. So let us quickly look at some of these operations. For example, if I just have an original pixel value, say f of x comma y, I can just map them to a new pixel by just multiplying the value by a constant and adding some other constant. So this is a simple linear mapping of all the pixels from one range to the other range. And there is also a transformation called logarithmic transformation, which is nonlinear. That means I'll take log of the original image and write it as a new image. And you may be wondering why a 1 is added here. This 1 is added only to take care of log 0 problem. Because the image f of x comma y gray level can even go to 0. So log 0 will be a problem. That is why if you just add 1 to that, you can avoid it. So you could see that when I take a logarithmic transformation of this image, what you notice is the contrast has improved as compared to the original image. So these are all some pre-processing steps that we do whenever we perform image processing. Another pre-processing step that we do is called histogram-based operations. We have two things. One is called histogram equalization. What we do here is histogram of the original image is actually made as a uniform histogram. In the second case, we are going to specify the histogram that we want to have it. Let us not worry about this mathematics. I just want you to show the results. See, you can observe here, when I take images at very bright light, this is what you are going to see. So you can observe here the image is mostly having pixels towards the whiter region. So if I plot the histogram of such an image, this is how you look at it. See, observe, this is the scale from 0 to 255. Most of the pixels are in fact occupying about 150 plus. So they are all bright values. Now, if I perform equalization of this, that means if I just try to stretch this histogram, which will start from 0 to 255, which is clearly seen here. So you will see all the pixels starting from 0 to 255. That means you are going to stretch this histogram or equalize this histogram to get almost a uniform type of histogram. So notice here, after performing histogram equalization, the visibility of the image is much better when compared to this. See, some brighter pixels are looking really very bright. Darker pixels here are really looking very dark here, even this region also. That means you have a good contrast compared to the image that you have here. So equalization is one of the pre-processing steps that we perform. Specification, see, observe that I have an image like this whose histogram looks like this. You have a Lena image whose histogram looks like this. Now suppose if I want to specify that the histogram of this image should have a shape like this. That means my target histogram should look like this. So if you perform this operation, this is what you see. So you can see there is a further improvement in the image compared to the original histogram here. So, so the difference is in histogram equalization, the target histogram is uniform, whereas in histogram specification, the target histogram is specified by the user. That is the difference. Just like the filtering that we do in one dimension, even in here also image processing, we have various filters like mean filtering, median filtering, max or min filtering, alpha trim mean filtering. That means the mean filtering, as you know, you use mean or average. Median means you use median of the pixels, maximum of the pixel or minimum of the pixel. I will directly go to the results here. So you can observe that there is a Lena image which is corrupted by Gaussian noise, and you can filter it by using an average filter. So you can observe that the noise components are reduced. At the same time, you should also notice that the image also is getting blurred. In this case, you have an image, in fact, corrupted with a specific type of noise called salt and pepper type of noise. I think those of you who teach image processing would be knowing this. It is just like you are sprinkling some droplets of salt and pepper on an image. You know, salt is white in color, pepper is black in color. So if I put such type of droplets on an image, some of the pixels will look white and some of the pixels will look dark. Hope you can see that. Such a noise can be removed by using median filter. Okay. Similarly, other images are seen here. Now, one of the requirement of image pre-processing is to enhance the edge information, because say for example, if somebody is working on character recognition or license plate recognition system, the edges of the text should be very clearly seen, so that you can recognize the characters without any ambiguity. So I need to perform such type of edge enhancement, for which we use a low high pass filter and use it carefully to enhance the edges. I will show you a very good application or an example. Please keep observing this image. This is a cat image. After I apply the head crispening, this is how you look at. So I'll just try to show it one after the other. So before, this is what it is, and after, this is how it looks. Hope you can see the difference in the enhancement of the edges. In fact, the hairs here, if you carefully observe, you could see the enhancement. I hope you can see the difference. So this is required, as I mentioned, when you are working on something like character recognition or license plate recognition, where edges are very, very important to you. We also, whenever an image is formed, it is a function of two, in fact, parameters. One is the amount of light that is falling on the image. Second one is amount of reflection that happens. So sometimes, because of non-uniform illumination, you would have an image captured something like this. So what you notice is, because there is a lot of reflection from this region, the edges are not clearly, in fact, captured. So such type of non-uniform illumination variation can be removed by using a filter called homomorphic filter. Hope you can observe the image is almost uniformly illuminated when compared to this. Again, the application of this could be, assume that you are working on face recognition system, and while capturing the face data, when you are trying to authenticate, probably the illumination may not be good. So it's always possible that your algorithm would not work when the illumination changes. So to make your algorithm illumination invariant, probably you may have to do such type of pre-processing before you actually do authentication. That means apply a filter called homomorphic filtering, which actually separately acts on the illumination portion and the reflectance portion, and you can carefully ensure that such type of illumination variations are taken care of. Okay. Another important topic in image processing is image segmentation. I think a lot of discussions can be done even in this area itself. Particularly, there is a lot of scope in medical image segmentation. Suppose if I have an image something like this, and you are asked to just extract the text information from the background. What we would do is, we will just, a simple method is put a threshold and say anything above the threshold is white and anything below the threshold is black. So you may be noticing here, because of the quality of the image here, where the illumination is varying, you may not be in a position to extract the entire or segment the entire text from the background. But if I use some local thresholding technique, that means I'll use some local image information and apply the thresholding, I would definitely be in a position to remove the background from the text. So image segmentation is another area of research. Then identifying various features like edges, corners, lines, and circles. Okay, so you can use various filters to find edges. For example, these are various edge detection filters. Okay, these are what you can observe here is, this is going to identify an edge along this direction, because you just try to find the difference between this pixel and this pixel. So if there is an edge along the horizontal direction, I can use this. If there is an edge along the vertical direction, I can use this. And slightly improved versions of this is a Sobel filter, which will give a more weightage to the center compared to the neighbors. So these are various gradient operators that are used to find edges in an image. I think there are some good examples that you could see here. Sobel, this is Previtt, and the well-known technique is scanning, and of course, Canny has definitely done better than Sobel and Previtt. Whenever I want to find the lines, example, you want to detect the shape of an object, you need to find the lines. You need to find the lines along all the directions. So we use Huff transform. You want to do circle, for example, you want to identify the shape. So you want to observe these circles here. That means the coins are to be detected. So we would use these various detection algorithms to identify the shapes. Okay, so more or less, even though I have not discussed everything, more or less, these are the various pre-processing steps that we would be following in image processing. Okay, so I need to go to applications part now. But I just want to give a break, and if there are any specific questions up till now, let me hear from you. Otherwise, we will see some applications. So, are there any specific questions from the audience?
Participants, if you have any queries or doubts, you can ask with the keynote speakers.
Good morning, sir.
Good morning.
Sir, what are the feature expects for medical images, sir?
See, medical imaging is in fact, it's another, in fact, huge area of image processing. It actually depends on what type of images you are talking about. For example,
CT images.
Okay.
CT images.
Okay. So in CT images, what is your, in fact, interest, region of interest?
Lung CT images, sir.
Correct. Lung CT images. So in that, what is your region of interest? Like, what do you want to identify there?
Tumor detection. Tumor detection.
Okay. So are these gray color images or color images?
Gray color images, sir.
Okay. So if gray color images are being used, one of the features could be the shape. Okay. The shape of the region of interest that you're talking about is one of the region of interest. One of the feature that you would like to use. Okay.
Yes, sir. Yes,
Another thing is, for example, within that small region that is of interest, you can probably try to identify what could be the statistical parameters. For example, the mean of that area,
yes,
the first moment, maybe the second moment. Okay.
Yes,
So you could use these as the features for probably detecting maybe some tumor or whatever it is.
Yes,
okay.
Sir.
Okay.
Yes, sir. Thank you, sir.
Yeah, good.
Yeah, sir, there is a...
Yeah, please go ahead.
Good morning, sir.
Can you say the difference between texture and untextured images? Question raised by the participant Uma.
Okay. So yeah, I think probably let me just go to an image which I was showing you, the Fourier transform. See here, what you see here is actually a type of texture image, because there is lot of variation in the values here. So you could see that at no region you have a smooth variation, whereas in this case, no, there is lot of smooth region here. See, observe here, observe here. So the texture is something where you have too much of variation. That means a very random variation of pixel values. There is not a smooth region that you could see. So these type of images are called texture images, and images like this where you have some variations only in specific regions, whereas in some regions the brightness level is almost constant or slightly deviating. That is the difference between texture and non-textured images. I hope I have answered your question. Did I answer the question or any further clarification is required?
Uma ma'am? Yes, yeah, she replied yes.
Yes, sir. Okay, thank you, sir.
Okay. Yes, sir, there is another question from the participant Indu D. Is threshold is used only for the image segmentation?
Please repeat the question, sir.
Yes, sir. Is threshold is used only for image segmentation?
I didn't get the question. What
Yes.
is the meaning of that? Of course, yes.
Yeah, threshold parameter, is it only used for the image segmentation, sir?
See, threshold can be used only in specific cases. You cannot use thresholding for segmentation for all the type of images. For example, if your region of interest is completely smooth area, then thresholding can be done easily. You can just apply a threshold, and anything above that you can rate it as black or white, and thresholding can be done. Assume that your region of interest is also having some noise-like structure. That means there is a variation in the pixel values. Then what happens is, if I just use a simple threshold, then there is quite possible that within the smooth region that you are trying to identify or segment, you would have a lot of variations. So in such cases, we use another method called region-based segmentation, where you just apply a condition that over this particular, in this region, if I allow a particular gray level variation, maybe some 100 to 150, I will just consider it to be one smooth region. So in such cases, you may have to use region-based segmentation. Thresholding can be done, of course, when your region of interest is smooth. The foreground is smooth. I hope I answered question.
Okay, so thank you, sir.
Fine.
Yes.
So,
Participants, any other questions? Yes, sir. Please.
So we'll go ahead with the applications. Okay, so next part of the discussion is some
Good morning, sir.
Morning.
Sir, I am Dr. Janagi from Mathematics Department.
Yes, madam.
Can you suggest any basic book to learn image processing?
Madam, there is a textbook by R.C. Gonzalez and Woods, image processing by R.C. Gonzalez and Woods. I think that is the best book for a beginner.
Okay, sir. Thank you, sir.
Fine, thank you. Okay, so thanks for the interaction. It's nice that we had some questions even in online mode of presentations also. So with this, let us go to the second part. Okay, so in fact, the initial part of the research in image processing was mostly into space research, where there is a lot of scope for sir, Rohit sir, are you there?
Sir, yes, sir. Okay.
Okay, I just want to attend a very important call. Can I just take a break for
yes, sir.
just 2
Sure,
minutes?
sure, sir.
Okay, sorry.
Yes, sir. Sure, sure. Sir.
Okay. I'll be back in just another probably 1 or 2 minutes. Okay.
Sure, sure, sure.
Sir, am I audible,
Yes,
sir?
sir.
Okay.
Yes, sir, you are
Sorry
audible.
for that. Okay, small disturbance. Is the slides visible? Can you just?
Yes, sir.
Yes, sir, it's
Okay.
visible.
So we are into the applications. As I mentioned, the preliminary stages of image processing research was on space. There is because whenever I capture images, particularly for space applications, it's an unintentional imaging. So there would be a lot of variations, like you may have some blurring that is going to be there. Because of atmospheric variations, there would be a lot of noise. And also, the resolution of the camera that was used for onboard satellite definitely will be of very low quality. So there is a scope for us to do research in this area, like how do I deblur or in fact restore such type of images? How do I perform denoising? How will I increase the resolution of the images that I have captured? Okay. So in this area, a lot of research has happened. We also have tried some techniques in our department. For example, this is one of the MTech project thesis that was, I think, probably somewhere in 2010 or 11, by name Varsha Vijay. She did her project under my guidance. She was an MTech student here. So what we have tried here is, given a degraded or blurred image, how do I restore? But the condition here is the blur that I am talking about is not uniform. That means it is spatially varying. See, the problem with spatially varying type of blur is you cannot use your simple convolution operation that you have used for linear time invariant systems. LTI systems are characterized by the impulse response. So I can easily find the output from by convolving the input with the impulse response. So that simple convolution operation is not possible because the blur that I'm talking about is spatially varying. I hope you can observe in this case, the blur on the left part of this Lena image is different from the blur on the right part. In fact, I have given this in the form of the variation in the blur parameter. So it's severe blurring on the right side compared to this. So we call such type of blur as spatially variant blur. So we applied some deblurring techniques on this and we could produce some nice results. As you can see, this is the restored image. And in fact, this was presented in a national conference in 2011. Then my first PhD student, Dr. Arvind, he actually did some work on image denoising. So the goal here is a noisy image is given to you. How do I recover the original scene from this noisy image? So of course, noise is random and you don't know the noise, and it may not have a parametric assumption. That means you cannot just assume that noise is Gaussian type of noise. So there are challenges, and we tried implementing some algorithms. In fact, we did it both in transform domain and even in spatial domain. And the results were actually published in two journals, one I think in 2012 and another in 2019. So there is still a lot of scope in image denoising because noise is not a very simple phenomena. You have to understand it, and also simple assumption.
Sir, your voice is not audible. Suresh, sir, we are not able to hear you. Participants regret for the inconvenience. So the major challenge is the connectivity issue. So I request you to please wait. Participants, yeah, resource person, our keynote speaker will join us soon. Yeah, here. So before starting, I would like to inform you that there is an inaugural function at 1 p.m. and even the AACT ATAL, there is an inaugural function will be held, which is will be uh, live streamed in the YouTube. So both the links will be shared. So I request all the participants to join the inaugural function at 1 p.m.
Hello.
Yeah, Suresh sir. Yeah, Suresh sir, you are audible, sir.
So is this video visible, sir?
No, sir. No video is no. Can you present it again, sir?
I'm just trying. Say I don't know.
Yes.
Is my slide visible?
No, sir. It's not
Okay.
presenting.
Then I think I have to share it again. But the share
Yes.
option is now disabled.
Disable, sir.
I'm not able
Okay.
to. Should I log in again?
Can you just log out and log in again, sir? Once. The participants request you to please stay back. Sir, keynote speaker will join us again. He's trying with to share a video. He'll come back. Yes, sir. It is to inform all the participants. Attendance form and the feedback form will be shared at the end of the session, at the end of the day, at the final session. Request all the participants to stay back. Please do not leave the meeting. Sir is
Yes, sir.
about
Yes,
to
sir.
join.
Yes, sir.
Thank you, participants, for your patience. Apologize, participants. There is I think there is a serious issue uh, from keynote speaker side. Request you to please wait. Yes. Yes, sir. Sir has joined.
Okay, sir. Sir, I'll share my screen
Yes, sir.
again. Okay.
Yes, sir. Yes, sir. Please.
Sir, is this video visible?
Yes, sir. Now.
Oh, okay.
Yes, sir. It's visible
Okay.
now, sir. Yes.
Okay. Sorry for this glitch. There was some issue with my Chrome actually. So what you could see here is, if you carefully observe, actually this video is captured from the height of about 20 feet from a flyover. So the intention here is to read the license plate of this vehicle. So as the vehicle is moving, so we tried applying is my slides visible, sir?
Yes, sir.
Yes, sir. It's visible.
Okay. Yeah, sorry for that. So this is actually the problem on hand. So we wanted to actually improve the resolution of the images. So as it is, the low resolution images look like this. Then we applied few algorithms, and this is the proposed approach. I hope you can clearly read this number as K8354, which was not possible from the low resolution images. So this is actually what we had done. And in fact, the complete modeling and also the algorithm is available in these two papers for somebody who would like to make use of the work. You can refer to this. And in fact, this transaction, IEEE transactions, has in detail discussed about the problems in super resolving the license plates, particularly in real traffic videos. So those of you are interested can go to these. And all of you know that biometrics is one of the vast area of research in image processing. So there are a lot of biometrics like fingerprint, hand, iris, face, of course, even the keystroke, signature, voice. So combination of these would help you in fact, pursuing research in the area of biometrics. And of late, because of this COVID, contactless biometrics is a very important area of research. Like how you can probably scan the fingerprint data without actually touching the scanner. So I think there is a lot of scope. And a lot of fingerprint verification methods have been, in fact, developed. And one of the application that I could show is this. Hope you can see. This is actually an ATM machine which works on the fingerprint rather than typing the password. So you can probably transact with the bank by just using the fingerprint in the ATM machine. So this was developed at IIT Madras for a rural area. It was developed, and in fact at SIT we also tried, in fact, developing an attendance system which will help a teacher to avoid, in fact, spending time on taking attendance. So the students actually developed a small gadget like this, which has a fingerprint scanner, which has a keyboard to actually match or test your algorithm, in fact, attendance. It also has a memory which will store the data. So you can enroll any student to the class. You can just, so that means my job is, as a teacher, I should take this to the class and give it to the student, and student will just give his or her attendance and pass it to the next student. So this way we have developed some authentication systems. Then, particularly face authentication at this current COVID situation would be difficult if somebody is wearing mask. So I think developing robust algorithms which can work even when somebody is wearing mask, because wearing a mask, people wear different type of mask, and wear the mask at different places. So in all these typical cases, your algorithm should work. So developing such algorithms, particularly in this current scenario, would be of great help. Then our students also tried developing a ration shop, which is a smart ration shop, which can work on biometric. That means face recognition was used. Lot of applications are available in robotics now in image processing. For example, all of you must be knowing that just to avoid contact with COVID patients, robots have been developed which can go and probably do the job of a nurse who will attend to a patient. So without having any physical contact, I think robots can help. So bringing some intelligence onto these robots would be of a great help. So people can use these. And of course, in stabilization of video, mosaicing, I think this has already come as in fact, a feature in a camera where you can produce a panoramic image of whatever you have captured. And this is another application for advanced driver assistance, which was developed by one of my student, Swati, who did her project, MTech project under my guidance. The idea here is you can automatically detect, that means when you are traveling, when you are driving, and when you are not cautious about the traffic signal points. So you can have an automatic system which will recognize and probably spell it out to the driver. So the driver need not look at the sign; he can just listen to the voice that is developed. So this was actually tested real time. In fact, it is also published in a IEEE conference in 2017. So where there are a lot of challenges. All of you know that you are actually capturing with an angle. Not only that, the boards would have been spoiled because of probably some way atmospheric variations. So how do I recognize such traffic signal? In fact, signs which will help a driver for smooth riding. Then in fact sorting, people use image processing. For example, there are a lot of videos here. For want of time, I'm just avoiding showing them. Different types of bearing was sorted by using a machine. Different type of pencils based on the color. Rice, automatically you can sort rice into good rice and probably not so good. And one of our student batch, they developed what is known as a areca nut sorting machine. I will probably just click on this video. Hope you are able to see the video.
Yes, sir, it's visible.
I'll just explain what this batch of students did is they wanted to sort the different types of areca nut after it is peeled out into different category. Like in fact, there are 4 different categories. So they just actually did this sorting. So Charlie is one of the category. So actually what they did here is they used the color information and tried sorting. That means they are replacing the manual labor by an automatic machine. Again, this is just based on color information. Of course, so there is a hardware where the camera captures based on the color. It tries to separate the areca nut into different categories. Then for advanced driver assistance, one of my MTech students, Dayanand Kumar, he developed a pedestrian detection system. So when you just are driving, suddenly if a pedestrian crosses the vehicle, so the reflex of the driver sometimes, if you are not quick enough to apply the brake, then anything can happen. So if you can provide an advanced driver assistance wherein the brakes can be automatically applied, so he worked on this pedestrian detection. This is also published in one of the IEEE conference. Then some students worked on detecting the potholes by using image processing. So you can just probably capture the video of the roads, and your algorithm tries to tell you what is in fact percentage of potholes that you have in that particular road. They're based on color image, but the shape here. Then some students worked on counting people in a big malls just to know how many are there within the particular time duration, how many have actually visited. This is again a BE project carried out by one of my project student group based on in fact the shape detection here. Then another set of students, in fact 2 versions of this project was done, which will help a blind person to identify some known some basic necessities when he or she is alone in the house. So they had actually in fact developed a system which can be just put on your chest like this, and it has a camera. You have a Raspberry Pi which will detect the data, and then it will guide the blind person where is that in fact article that you are trying to search for. For example, if the blind person wants to use the restroom, it will detect the symbol of the restroom and guides the person. If the blind person wants to probably get hold of maybe water bottle or maybe some food, so based on the necessity, this helps a blind person. Again, we have actually published this in an IEEE conference. Then, as somebody has already pointed out, medical applications, there are huge applications in medical imaging, because there are so many different types of images that you capture, like MRI, X-ray, OCT, ultrasound. So lot of scope in processing medical data, because if you want to help a radiologist so that he can easily detect a particular disease and get a report of out of the images, it would be good to have image analysis. So one of my PhD students, Renikalata, she did some detailed analysis and also did some segmentation and also classifying images using some classifiers. Then very recently, one group of BTech students, they worked on hand gesture recognition, which could be used for conveying information to somebody who is using sign language. So different signs are recognized and you just convey the information based on the sign that you show. This is very recently published in one of the conferences, IEEE conferences. Then my current PhD student, Shilpa Shri, she is working on, again, medical image analysis. Particularly, we are working on analyzing the corneal images. Of course, we are using some machine learning techniques where you would be recognizing, in fact, segmenting these cells, and based on the shape and also the number of cells and also the issue that you have, you can identify whether it is a healthy corneal image or not. In fact, this is in tie-up with an hospital at Madras, Shankar Nethralaya, and also a professor from Indiana University. So this is a joint research work, And some outcome of this is already published in one of the journals very recently, Translational Vision Science and Technology. So more or less, I'm done with the applications because of some time lapse because of the technical issue. Some videos I have intentionally not shown you, but that is okay if you just have an overview of where all the image processing is used. I think those of you who are interested in this research area can take it further. Okay. Hopefully, I think this is my last slide. So I always conclude with this image in the end because sky is the limit. I don't think there is any end to the research in this area. So feel free to go ahead. I think a lot of good sessions are planned after this on machine learning, particularly on industry from industry. So I think I wish participants to make best use of the basics that we have covered just now, and also the knowledge that you get through hands-on to probably take this area further. So with this, I think I am done. If there are any specific questions, we can have it.
Some participants had raised their questions. Participant by name Nikhil Agarwal, which algorithm is best suited for PCB fault detection? PCB fault detection.
See, I think of late, most of this detection algorithms, they are using CNN, because if you just train for various faults, that means if your training data is available, I think you can definitely train all the images with different faults using a CNN, and probably that could okay, help in detecting because it all depends on what type of faults that he is talking about. But I think if you have the data, probably using CNN, it could be done easily.
Sir, another question from the participant Umasi. Question is, can we merge smart grid with image processing?
Smart grid. I just want a little more clarity what she mean by smart grid.
Uma ma'am, can you elaborate your question?
Sir, can we merge these two concepts, sir? Smart grid and image processing.
No, frankly speaking, I am not aware. I'm not aware of smart grid. So if you just tell me what is smart grid, I can tell you. Because I have not used
in electrical engineering side, the power system is calculated using the smart grid, sir.
Okay. Is there any? Yes, madam. Is there any scope that you will get some images there in smart grids? Because I.
Yes, sir. In power system, suppose some failure it occurs, means we can capture that particular image. Then after that we can analysis what is the problem under, or what circumstances, or what are the issues behind these images.
Yeah, see, if you have images, definitely image processing can be used anywhere and everywhere, because there is no limit. You have seen a lot of applications starting from medical, healthcare. So many applications are there. But as on now, because since I have not much knowledge about smart grid, I cannot guarantee you that it can be used. Probably we can discuss further. If you can share some images to me, I can help.
Yes, sir. Sure, sir. Can we share your mail ID, sir?
Yes, I think in my title slide it was there, I believe. Yes.
Okay, sir. I can take snapshots, sir.
Yes.
Screenshot. Okay, sir. Surely I will contact you, sir, after this course, sir.
Okay, man. Okay.
Thank you, sir. Okay,
sir. Yeah. Another question from the participant is once. What are the different publicly available data sets for space research?
See, I have actually not personally worked on space images. Because frankly speaking, my area of research is basically on developing algorithms for restoring or enhancing the image. It's more of model development. So we didn't work much. Only off late, I'm using the database for this hand gesture recognition and also. Okay, but I can probably because I have few experts who work in ISRO. So I think let the participant contact me separately. So I will try to get some information from these experts and let him know, because I have not worked on space images.
Thank you, sir. Sir, I will contact you. I'm
Yeah,
Professor Deshpande from Ahmednagar. I will contact
okay,
you.
sir.
Thank you.
Sure, sir. Thank you. Thank you.
Yeah, sir. Another question is from Shubha KG. What are the techniques or domain that can be interconnected with medical image analysis, mainly glaucoma detection and classification?
Is the question complete or?
Yes, sir. It's done. What are the techniques or domain that can be interconnected with medical image analysis, mainly glaucoma detection and classification? This is the question.
I don't know whether I think I've not understood the question properly. I think because is that what are the different algorithms that can be used or?
Shubha KJ participant, can you just explain your question? Can you just elaborate?
Good morning, sir. Sir, actually, what I'm asking is there any other domain that can be interlinked with the image processing?
Madam, for glaucoma detection, is it?
Yeah, actually, I was trying with nanotechnology.
Okay.
Yeah, is there any other technologies or any other domains that can be interlinked?
Madam, I think our physics department, they are trying to develop some sensors which can be used particularly for, in fact, this eye movement and all, like eye blinking and all. Okay. So they were telling that some nanomaterials are being used to develop some sensors. So vaguely how I can answer your question is probably developing some sensors using nanomaterials and capturing data by using that sensors and then doing an analysis on these data probably would yield some fruitful result. That is what I can probably vaguely answer your question, because I don't work on nano materials, but of late I'm just guiding an eye blind detection project to my students. So I interacted with our physics department. His name is Dr. Sridhar. So he developed some sensors basically on using nanomaterials. So such type of sensors developed exclusively for capturing some information, okay, would probably help you in integrating your nanotechnology with image processing. That is what I think at this point I can answer.
Sir, another question.
Yeah.
Yeah. Thank you, ma'am. See, another question. Basic data sets, is it helpful for experimenting on MP? I didn't get. The question is, basic data sets helpful for experimenting?
Sir, any data set which is validated by other researchers would be definitely helpful. But what I suggest is, see, it's always better, see, first of all, validate your algorithm using the standard data set that is available, but try to develop your own data set for whatever application. For example, just to give you my own experience, this hand gesture recognition, even though there is huge data that is available, we also developed our own data set. Because in fact, while generating our own data set, you will learn a lot of pre-processing steps that you would be using. And also, that would, in fact, ensure that the algorithm is helpful for even the other data also. Sir, are we connected?
Yes, sir. Yes, sir. Yes. Yeah. Participants, is there any questions to be asked? Yeah. Okay. Yes, sir. So, sir, another question. So,
So
please
if
suggest
there are
the.
no questions, yeah.
Yeah, one more question, sir. Last one. Please suggest the
Yeah.
artificial intelligence technique for combination of image processing and statistical analysis.
Textbook, I think I had to
A
look for
technique,
it.
artificial intelligence technique for the
Okay.
combination of image processing and statistical analysis.
Statistical analysis means statistical analysis on what?
The participant by name Indu, can you just give a clear idea? Okay, so maybe.
I think, sir, what you can do is just share by email ID, or
Yes, sir.
you can
Sure.
even share my phone cell number also to the participants. Let them
Sure,
call
sir.
separately, because when they ask questions, they would be keeping their research area in mind, ask the questions. So sometimes it would be difficult to answer unless I know the background.
Sure, sir. We'll share your contact number
Okay.
and
So
mail ID to the
yeah, let them
participant.
contact me.
Yes.
So I
Sure,
think
yes,
thank
sir.
you. I
We'll
think
finish the session, sir. We'll close the session.
I'm really happy that there were so many questions and the participants are interacting. This actually shows, even though it's an online, and also we had some technical glitches, so they are still with us and asking questions, and I really appreciate their interest, and I wish all of them all the best. And I thank all the organizers of this FDP for giving me this opportunity. Uh, but for this online mode, I would have been very happy to meet all of you personally at Nagarjuna College. Hope I'll get another chance sometime when this pandemic is not there. Okay. Thanks once again, sir. Thank you very much.
Thank you, sir. Thank you, sir.
Thank you.
Yes. As a vote of thanks, I sincerely thank Dr. K.V. Suresh, sir, for sharing your invaluable information with us, sharing the basics, terminologies of image processing, different filtering techniques, and also quoting different methodologies by applying with different images. Thank you, sir. In spite of your busy schedule, accepting our request for conducting a session for us. Thank you very much, sir.
Thank you, sir. Thanks for the opportunity.
Also, I thank the participants for your active participation. Also, to inform, the next session will start at exactly at 11:30. Uh, thank you, keynote speaker session, sir, KV Suresh, sir. So we'll
Thank you, sir.
surely get
Thank you.
contact
Thank
with
you.
you, sir. Sure. Thank you,
Thank
sir.
you, sir.
Thank you so
Thank you.
much.
Thank you very much, Suresh, sir. Thank you very much, Suresh, sir.
Thank you, Nagesh. Thank you. We'll meet sometime, Nagesh.
Sir, sure, sir. Sure, sir. Thank you very much, sir.
Okay, I'm really proud to see you as head of the department and leading the team. Thanks.
Thank you very much, sir. Thank you very much for your continuous support. Thank you, sir.
Thank you. I think Mutana should, Malana should also be there. I thank Malana also. Thanks, everyone. Okay, I'll take leave now.
Sure, sir. I'll convey.
Okay. Thank you.
Participants, the link remains the same. It will be shared again in the WhatsApp group, so you can join exactly at 11:30. Thank you. Thank you so much, sir. Thank you for your participation, sir. Thank you. I thank all the participants.
Sir, I have a question. Attendance will be conducted in each session or the end of the means last
No,
session?
sir. Last session, sir. At the end of the
Okay.
day, in the last
Okay.
session.
Thank
We'll
you.
also share the same attendance link in the group also, sir.
Okay, sir. Thank you.
Thank you. Thank you for your participation, sir.
I request all the participants to stay for some time. 11:30 will be starting the session 2. Good morning, everyone. Hope I'm audible, right? Am I audible? Mhm. So we'll be starting session 2 of day 1. A very good morning to everyone. I'm Vicky Prakash, Assistant Professor, UNC Department. I wholeheartedly welcome you all for the session 2 of FDP, on machine learning applications and image processing. It gives me an immense pleasure to welcome our speaker, Mr. Rakshit B.S. from Fourier Technologies, Bangalore. Welcome you, sir. I hope Rakshit sir is there. Rakshit sir.
Hello, ma'am. Good morning. Am I
Yeah,
audible to you?
Yeah, sir. You're audible. Thank you. Welcome you, sir. And I take this opportunity and I'm privileged to introduce our speaker, Mr. Rakshit B.S. Here is his brief intro about Mr. Rakshit B.S. Mr. Rakshit B.S. is the Senior Application Engineer for Math Work Products at Fourier Technologies, Bangalore. He holds a BE degree from GWSIT, Karnataka. He has 6 years of extensive experience in technical education. He is currently providing engagement and solutions to educational institutions as a part of Fourier University program. He has technical hands-on expertise in MATLAB and Simulink. His area of interest are power electronics, control systems, fuzzy logic, image processing, computer vision, machine learning, deep learning. Now I would like to hand over the session with this brief intro. I would like to hand over the session to Mr. Rakshit B.S. Sir, over to you, sir.
Yep. Thank you very much for the warm introduction, ma'am. So let me, welcome all the participants once again to this session. So just give me a moment. Let me quickly share my screen and let me quickly start the session.
Yes, sir. Yes, sir. Please.
I hope the screen is visible to all the participants.
Yes, sir. It is visible.
Yep. So welcome everyone to this particular session. So in this particular session today, we'll be discussing on the image processing workflows. So what do you mean by, what is the toolbox that is available in the MATLAB? We'll be using MATLAB as a tool to implement this application. So we have, I'll be part of 3 different sessions. So in this particular session, I'll be focusing on the image processing aspect, and post which we have second session where I'll be discussing on the aspects of machine learning, and also I have one more session on 19th, so where I'll be discussing on deep learning aspects as well. So this is the basic whole idea behind the 3 sessions which I have planned here. So in this particular first session today, we'll be focusing on the image processing aspects. What are the workflows that are available, which helps us to simplify the implementation, and also we'll be focusing on once we discuss these workflows, I'll be also discussing on a few set of application which helps us to implement these image processing workflows in a simple manner. So keeping that in mind, before we start the session, let me give us a quick introduction to our organization Coral. So our Coral organization is basically handling various aspects. One of the major aspect it handles is the manufacturing and product development. So where in which we are majorly focusing on development of major of electronic projects for defense and aerospace based domain. And one more important domain is we have IP on video related technology as well. The one more important area we do is representation and distribution. So where in which we partner with various private organizations as well as government organization and educational institutions, and we work with them in a very seamless manner. Along with that, we also have training department where we focus on corporate and student training as well. Now coming on to one of the a quick overview of major projects we are working on. So we majorly focus on the aerospace and defense based projects where we do work with most of the defense projects in our government organizations. So there's one more interesting project which is happened in USA where we are developing the robotic operating room. Along with that, so we are also part of the Ashwini Radar project, which is one of the pride factor for our organization. Now, having said that, we are also a part of representing various principles. So these are few set of snapshot. In that, we are also team partnered with MathWorks. So having said that, so now let us come to the agenda of our session. So the agenda of our session is pretty much simple. At the very beginning, we'll be getting introduced to the image processing toolbox, and we'll also give a quick overview of what do you mean by MATLAB, how the interface looks like in a very quick time. Once that is done, we'll be focusing on the first simple aspect, which is basically the importing and exporting operation with our MATLAB, how we can import an existing image if required. If we need to export our image as an external file, how we can do that in a very simple fashion. Once we do that, we will be moving towards the image processing workflows. Like, if I want to visualize the image histogram, so how I can do that. And based on that, if I want to do something called as image histogram equalization, which is one of the simple pre-processing techniques available. So we will be focusing on that. We'll be understanding what we mean by this histogram equalization. So why this is important for us, and using our MATLAB, how we can do this operation in a very simple fashion. So that is what we will be focusing with. And once we complete the histogram equalization concept, we will be moving towards the thresholding concept. So which is also equivalently important for us in terms of the image processing techniques. So once we understand image thresholding concept, we will be moving towards the edge detection, which is also one of the important aspect in terms of image processing, especially when we are focusing on applications like machine learning or deep learning as the end implementation. So edge detection is also one of the important technique that we can apply. So as we move towards the implementation of applications, along with that, we also have the image morphological operations, which is available to us, which we'll be discussing in a very short time. So along with these workflows that we have discussed here, I'll be also showing you an application implementation where we'll use these few set of these workflows and we'll achieve an end result. So that is also something we'll be discussing post these workflows that we have implemented. And also along with that, so I'll be also showing you few set of resources that are available. If you are new to MATLAB, if you are new to this image processing toolbox, so what are the resources that will be available to you quickly, so that you can get started with these kind of applications in a simple manner. So that is also something we'll be discussing at the end. So now, having said that, so let us quickly have a quick introduction about the image processing toolbox. So if you see the if you have already gone through the image processing toolbox, this may not be very much new to you, but let me also give you a quick recap and a quick introduction. So basically, image processing toolbox helps you to achieve various image processing application, such as if you want to do analysis of a given image, you can do that very quickly. Even if you want to do segmentation of an image based on your requirement, you can quickly do that as well. Along with that, we will be also able to do image morphology. You can apply statistical techniques for our given image, and we can get those statistical results for a given image in a very simple manner. Along with that, we can also do measurement. So we have inbuilt apps available with the help of which we can easily achieve the measurement in a very simple manner in any given region of interest. Along with that, so if you want to do we have developed a specific algorithm, and I have a set of images and I want to apply that particular algorithm to all those images at a single time. So we can do that. We have something called as batch processing, with the help of which we can apply the same specific algorithm to a given large set of images, and we can achieve the results in a very simple manner. And even if you want to implement applications such as image registration, we have inbuilt functions available which helps you to do that in a very simple way. So along with that, we were discussing only for 2D images until now, but even if you are focusing on 3D images, so such as medical images, for example, so even we have MATLAB functionality support available to work with 3D image processing as well using our image processing toolbox. So that is something pretty much interesting for us. And along with that, so even if you want to do other applications such as image filtering, image blurring and deblurring, and geometrical transformations for any given image, so all those applications can be automatically achieved with the help of inbuilt functions that are available for us. So along with that, even if you want to implement your applications to any particular target hardware, maybe you want to implement this on Raspberry Pi, maybe you want to deploy this on GPU boards. So we have dedicated coder products that are available, and even our toolbox supports you to supports for the deployment of your application on target hardware. Along with that, even if you want to do automatic code generation, uh, you know uh, you can use our coder product, and we can easily do the automatic code generation for the target hardware in a very simple fashion. Now, having said that, so what are the various set of images that are supported in our MATLAB? So you can see there are huge set of data support in terms of data types of images which are supported here. So maybe it is a bitmap image, maybe the image you're handling is a GIF image, maybe even it is a HDF image format, PNG. Almost all the data types which are available with the it is automatically supported. And along with that, even if you're working with raw image data files, even that is also supported in a very simple way. So along with that, even if you want to see the support for DICOM files, which is the medical image files, right? So even that is automatically supported. So even we can deploy import a given DICOM image, and we can apply some pre-processing, and also we can export our pre-processed DICOM image as well. So even we have inbuilt functions which support reading and writing the DICOM images in a very simple fashion. So having said that, so now let us quickly go through the overview of the very simple functionalities of the image processing toolbox. So this is a very simple first example. So where I'm taking the function which helps us to import any given image file. So how we can basically import any given image file? So the inbuilt function which helps us to import any given image file is basically called as imread. So which is basically reading our given image file, and it will basically create a simple variable, whatever the variable when we provide here with that name, it will just keep that particular image file to be available within inside our MATLAB in a very simple fashion. So that is the simple process of working with our images. So let me just quickly execute this, and let me just show you what will basically happen. In our case, if you are able to see here, we are creating a simple variable with the name I, right? So let us see where this particular file exists in our case. So let me just quickly magnify a little bit, and let us move towards this window called as workspace. So whatever the files you import in your MATLAB, all those variables that you create, it will be automatically available in our workspace. So we have other set of variables that are available here. So let me clear those variables, and let me keep only those variables which are necessary for our first example here. So let me just re-execute that and let me bring here. Now you'll be able to see I have only single variable which is having the variable I. So which was the, which was basically importing this file with the extension .tif. So that particular image is imported to my MATLAB. So how I can verify that? You will be able to see whatever we are importing, it should be available in our workspace with the given variable name. Whatever the variable name we have specified, it will be automatically available. And along with that, we can also see here. So this particular image is not a scalar value. It has multiple element values. So the total size of this particular variable is 256 cross 256. That means the image which we have imported into our image is having the resolution 256 cross 256. And along with that, the data type, it is mentioning that the image is represented by unsigned integer 8-bit data format. That's all. So all those description will be automatically available to you, and you can easily make sure that whatever your the image you want to import into your MATLAB workspace, it can be easily imported in a simple fashion. Now, having said that, let us go back to the normal view and let us see if I want to display the image. So if whatever the image I have imported into my workspace, sometimes you may have multiple images at your hand and you are not sure whether you have imported the proper image or not. So in order to verify that, we have this function called as IMShow, which helps us to display any imported image, whatever the images we have imported. So if you want to display any one of the images, so we can easily do that by using this function IMShow. That's all, as simple as that. And you will be able to see the particular image which you have imported. In our case, we have given the variable I once again, and you are able to see we have the image of the cameraman to be available, which is a verification that we have properly imported the image in a very simple fashion. So along with that, now, so we have other workflow as well. So let us quickly go through that. So in the other workflow now, what I want to do here is I want to change the resolution of this image. I don't want this image to be having 256 cross 256. I want to resize this to a different resolution. So how I can do that? So we need to know what is the exact resolution of the imported image. In our case, we were able to see the resolution in our workspace itself, but how I can capture that as a value in our case? So we can do that in a very simple way. We have this inbuilt function called as size, which will basically capture the total size of our given data. So since in our case we already know all the pixel values of our given image will be captured as an element of a matrix, right? Since that is the case, we can automatically use this inbuilt function, and we can just pass our imported image, and it will basically give us the value to be stored in our user defined variable. So let me just execute this so that this variable will be automatically created. Now we are able to see in our workspace, now we have this im size variable imsz, which has this array value 256 and 256, which is basically the resolution of our versional image. So along with that, so before we do image resizing, so even if you want to check the other important information pertaining to that particular file, we can do that. So we have this file called as imf-info, which helps us to capture any other information that is related to this particular image. So if I pass this cameraman.tif, which was the image which we had used for importing, so you'll be able to see it will show us the exact location where this particular image has been stored. I was talking, this is an inbuilt image, right? So you'll be able to see this image is available in this image processing toolbox itself. So which is basically an inbuilt image that is available automatically. So other meta information such as what is the total size of this file, so when was this file last modified, so what is the resolution of this particular image, So what is the total bit depth of this image, and what is this bit rate of this particular image. So all those particular information will be automatically available to you. So you can easily go through all this information before you import, and once you have the proper image available to you, you can make use of image read, and automatically if you want to display that image as well, you can use IMShow, and you can easily import that image in a very simple manner. Now along with that, now I was talking about resizing our image, right? So we can do our resizing of our image in a very simple fashion. So suppose if I want to resize this 256 cross 256 image to maybe 100 cross 100. So how I can easily do that? So it is pretty much easy. So I need to create a output variable where I'm just storing a the resized image. In my case, I'll be creating this variable called imres, which will basically keep my resized image to be available. Then automatically I have this function called as imresize. So you will be able to see this particular function. If I open the function bracket, it will be showing us the input arguments that this function takes. So this particular input function takes the original image which has to be resized, and what is the the resolution, end resolution, which has to be resized with. And if you want this resizing to be happening in any particular method, so you can also mention those method as well. In our case, I don't care whatever the method that it will take. I am only focusing on resizing my image to the end resolution of 100 cross 100. So that is my end result I want. So let us just execute this and let us verify whether this happens or not. So let me just quickly execute this. So yes, we don't have this function variable a available. The image which is totally available to us is letter I. So let us use that. And in order to suppress this unnecessary output, so let us just use semicolon. And now you will be able to see I have created a variable with the name imres. So we know already how we can check out the resolution, right? Either we can check in the window of our workspace, or we can use this particular function called as size. So since size will be giving us the output in the script itself, let us use that. And let us see what will be the output. For our imres, you will be able to see now we have this new variable available in our workspace, and the resolution of that particular imres image is basically 100 cross 100. So this is how you can easily do resizing of any given image very quickly. So using our function, automatically you can take our image and you can easily do the resizing. So let us just view the image of our imres, and if I execute this, you will be also able to view the image of that. Now you are able to see we have the same cameraman image, but now the total resolution of the image has been shrinked to a smaller resolution. Instead of 256 cross 256, which was the original resolution, now we have a smaller shrinked resolution, which is basically 100 cross 100. So this is how you can easily resize our given image. Either you can use the end resolution can be bigger than the given image, or even it can be smaller than the original resolution. So you can do resizing in both the ways, and you can easily use this function in a very simple fashion. Now along with that, so when it comes to these kind of images, you can also work with this in a whatever the normal mathematical operations we can do for any given numbers, we can also do that for any given images as well. So if you want to take any scalar value, and if you want to add to each and every pixel in your given image, we can do that. If you want to subtract that, we can do. If you want to multiply, and even if you want to divide as well, we can do all those operations in a very simple fashion. Now let us quickly show that. So in my case, I'm using this particular option where I can choose my scalar value. In my case, I'll be choosing the scalar value to be basically maybe let me choose the scalar value to be plus 50. Yeah, so if I choose this as a scalar value, and if I do, once I select that, you will be able to see I'm executing this complete script, automatically using this particular control option. So automatically it is taking this updated value and it is executing all this operation: multiplication, subtraction, addition, division. And if I see the result after doing the scalar addition, now you will be able to see, if I just compare my original image and if I check the resultant image after addition of the scalar value, now you will be able to see this image is having much more bright, much more better brightness compared to the original image. The reason why we already know, right? Because since we are adding a specific scalar value, so all the pixels are moving towards white region, and that is the reason why you are able to see we have a much more better brightness in this particular image. Similarly, I have also done the subtraction operation for the same scalar value, and you will be able to see, so this image is much more a little bit darker. The reason why is, once again, since we are subtracting this, so it will be moving towards the dark region, which is towards the color black, and we have this darker pixels available in the complete image. Similarly, if I multiply my whole scalar value, you are able to see each and every pixel in my image are totally resulting more than 255, which is the 256, which is the maximum value our pixel can take, which is the value white. Since that is the case, all the pixels are getting truncated to the maximum value, and we have a complete white image available to us. Even in the opposite case, even if we do the division, so once we do the division, we are getting most of the results in terms of 0. Since that is the case, we are able to get this value to be truncated to 0 for all the pixel value, and we have an image of total black. So this example, I just wanted to show you that even if you want to do any quick scalar operation for any given image, you can automatically do that using simple normal mathematical operation like plus, minus, asterisk, and divide symbol. We can automatically do those operations and we can get the results in a simple fashion. Now coming on to the final aspect in this particular first example, I have done the necessary pre-processing whatever I want. So for example, I had a resized image in the variable imres, right? I want to store this resized image and as an external file to be available for me. How I can do that? So we have this function similar to the function imread. We have this function called as imwrite, which helps us to export our available image in the workspace to be available as a external individual file in our existing current folder. So that is what this basically helps us to do. So in our case, I'm telling to the function that, so in my current existing workspace, I have this file called as, I have this variable called as imres. So this is the variable which has to be exported as an image. And the file name of that particular image which has to be exported is basically with the file name cameraman. And along with that, we have flexibility to change the extension. Our original image had .tif as the file extension, right? But in my case, while I'm exporting here, I have flexibility to change the file extension as well. In my case, I'm just telling that this particular image now has to be exported as .jpg. So once I do that, so let me just quickly execute by showing you the end result. So let me quickly execute here. So once I execute here, so it will take a few seconds of time, and after that you will be able to see, in my case, a file name with this image has been automatically available to me. And if I use the magnifier a little bit, you'll be able to see in the preview window we have the same image available, which is our cameraman image, and also the resized resolution for this image was 100 cross 100, right? So it is basically available. So we have this cameraman.jpg file available in my current working folder, which is the exported image. and it has all the, which has the same image and the same resolution to be available for us in a very simple fashion. So similarly, along with that, even if you want to achieve this particular image to be exported in a particular destination location, now you have flexibility for that as well. So you can select the destination, your location. If you have selected any particular location like C drive, in that if you have already kept a destination with the with the folder images, and if you want to store there whatever the pre-processing you do, you can automatically choose that. And if you do that automatically for that particular location, so you will be able to see that particular image will be exported. In our case, since I want this to be available in the current folder, I will not choose any destination location. I will just mention the file name. By doing that, automatically it will choose the destination location to be the current working folder, which you will be able to see in the left section, all the files, whatever the location I'm selecting here. So in that particular location, that particular file will be automatically created, and that file will be automatically available to us. So once that will be available in our current folder, we can automatically move to that, move that file to any destination location we want, right? So that is how our IMWrite basically, works in a simple fashion. So I hope everybody has got the idea of the basic functions using our image processing for, toolbox. So if you have any kind of questions, please feel free to put up that question. Now let us move towards, yeah.
Sir, I had a question. I am actually very novice in this field, so I just wanted to ask that while exporting the images, can we give our desired format, the image format?
Yes, that is what I was talking about. It is not necessary that while you are, if for example, see if you are able to see here, the image format which I had used means the original file had an image format of .tif, which is basically tagged image format, right? But while I was exporting the same file, for which I had done simple pre-processing of image resizing, and once that resizing was done, I'm using the same resized image variable for exporting the image. Now here, while I'm exporting, I will be having freedom to change the image format. If I want the image to be bitmap file format, I can choose the extension to be .bmp. If I want the image file to be JPG, I can choose the extension to be JPG. If I want even the exported image to be having the original image format itself, I can keep even here also cameraman.tif. Once again, it will export with the same extension whatever I define here. That is how IMWrite is flexible with the extension we define here. I hope I have answered your question.
Yes, sir. Thank you very much.
Sure.
So one more question, sir, from Meena Divya.
Okay.
She's asking, can we have a demo for a DICOM image?
Yeah, I can show. I can have a demo. That is not a huge problem. I have a DICOM image available to me, so I can show how I can use this inbuilt function, how I can import the DICOM image. I can show that. I have example for that. I'll be showing that at a later stage if that is not a problem.
Okay, sir. Thank you.
Sure.
Hello?
Hello, ma'am.
Sir, how we can interface the MATLAB output to the FPGA board, sir?
I'll be talking about that, ma'am. Basically, in order to interface your means basically when you're saying interfacing, you are talking about deploying your applications onto a FPGA board, right?
Yes, sir. Yes, sir.
So when it comes to that, we have a dedicated toolbox called as HDL coder toolbox. You have to utilize that along with image processing toolbox, whatever the algorithm you're developing using that. So you have to use HDL coder toolbox, which helps you to do automatic code generation for HDL as well as VHDL as well as Verilog. You have option while you're doing the automatic code generation using HDL, and you can, using that toolbox, you can easily deploy that into your target FPGA hardware. So may I know which particular hardware you are working with, ma'am?
Zybo board, sir.
Okay, Zybo board. Yeah, you can. We have support for Zybo board as well for our HDL coder toolbox. You can use that particular HDL coder, and we have something called as in your MATLAB. You should also install the add-on for your particular target hardware, and once you install the particular MATLAB coder support package for that particular target hardware, automatically you can do the code generation for that particular target hardware itself, and you can easily deploy that into your hardware. So if you still have any, yeah, so that is a simple overview. But if at any point, if you come across any issues while you are utilizing this particular toolbox, I'll be sharing you my email ID later as well, so you can contact me. I'll be able to help you with any kind of issues you're facing as well. That should not be a problem.
Thank you, sir. Thank you.
Sure. So I hope, so now let us move on to the next part. So before we move to the next, part, we'll have a quick check with this. So now, in this particular case, now what is the idea, for this particular example? So one of the basic, image processing techniques that are available. There are various techniques that are available in our case. So one of the technique I'm using here is a image enhancement technique. There are various image enhancement techniques that are available. So in one of that most simplest and easily commonly used technique is called as histogram equalization. Now, what do you mean by histogram equalization? So it is a technique which helps us to improve the contrast of our given image. So that, in a very simple way, if you want to say what you mean by histogram equalization, it is as simple as that. I have given a much more detailed explanation in this particular file. I'll be sharing you all these files post the session as well. So if any people are new to this histogram equalization technique, it is not much complicated. You can go through that particular given given explanation later as well. And also for the function I'm utilizing to achieve histogram equalization, so no need to write any algorithm in our MATLAB. We have an inbuilt function available for us as well. So if you want to go through that function in a detailed manner, I have also given the hyperlink for that function in our case as well. So you can go through that at a later stage, and you can utilize your function for your own user specified manner. But in our case, what we'll be doing here is we'll be seeing how I can use this particular function to do histogram equalization for a given image, and how it is basically helping us to improve the contrast of our given image in a very simple fashion. So in order to do that, I'm using a simple image, so which is again here an inbuilt image available in our image processing toolbox, so which is having the file name POUT. So again, this is a TIF image, so I'm just importing that into my workspace. So I'm giving the variable name img to do that. Along with that, to just verify whether I'm properly loading the proper image or not, I'm just visualizing the given image as well. So here you will be able to see this is the image which is available to us. So now this image is having low contrast image. So for example, if I focus on this right top corner region, the region, especially the region where this particular child who is standing in this image, post his hair, there is some region where the background as well as his hair looks almost similar. We'll be not easily able to differentiate where this particular boy's hair ends and the background image begins. That is what is basically the simple definition of a low contrast image. So in a given low contrast image, we will be not we will not be able to differentiate between the foreground region of the images and the background region of the images, which is not good for any pre-processing techniques that we will apply. For example, if we go for edge detection, as we will be discussing further, or if we will do something called as thresholding, which we will be also doing as we go further. So if we have a low contrast image like this, the result of those techniques will be little bit poor compared to if we apply the same image with an enhanced technique. That is where before we do any particular image processing, so if the given image is having poor contrast information in the given image, similarly like this, we will always use some kind of image enhancement technique which helps us to improve the quality of the given image, so that we can take that improved image and we can apply other further pre-processings techniques in a simple fashion. So that is why I took image enhancement technique as the first step, because that will be the common application that we will do if the given image is not suitable enough for us to do given any pre-processing techniques. So in my case, I'm just visualizing the histogram. So I was talking about that as well in the agenda, right? We will be talking about how we can easily visualize the histogram of a given image. So we have this inbuilt function called as IMHist, and I'm just passing that image which we have imported just right now. Sorry for that. Yeah. Once I do that, now you are able to see we have this particular histogram available to us. So our given image is a grayscale image, and you are able to see we have in the x-axis the total lower darker pixel region as well as the brighter pixel region, and also we have normal grayscale region in between as well. And now if I take the histogram plots here, we are able to see most of the pixels are concentrated only in the irregular grayscale region. We have very less amount of pixels in the brighter region. We have almost no pixels in the darker pixel region. So this is basically how a low contrast image will be. So we can easily identify whether a given image is a low contrast image by using this simple histogram. And for any given low contrast image, even you will be able to see the histogram will be similar to this as well. Almost all the pixel will be concentrated only in the grayscale region, and will be not having sufficient pixels in the brighter pixel region and in the darker pixel region, which will give us a simple result like this, where in most of the cases both the foreground and background region will look like almost same and will not be able to differentiate that much easily. So now I want to improve this quality of the image. So in order to do that, we have this particular technique which I'm employing here, one of the image enhancement technique, which is basically the histogram equalization. So in order to do that, so we have this inbuilt function available to us, so which is basically hist eq. I'm just utilizing that, and I'm just telling this is the low contrast image I have available to me. I want just apply histogram equalization to this given image, and whatever the improved image that will be available to me post this, I want this to be available in this new variable, just simple definition. And once I do that, I'm just displaying the the histogram equalized image. In the second stage, you will be able to see the quality of image is much more better, right? We are able to differentiate different regions between this image, especially if I consider the foreground as this particular child. We are able to define the boundary within this region by ourselves in a very simple fashion, and we are especially the top right region here, right? We are able to even differentiate the hair region and the background region in a much more better fashion compared to the old image. So that is what this basically the histogram equalization technique will do. So it will basically expand your histogram in such a way that it will be able to give provide pixel in the bright region as well, in the darker region as well, which will basically improve the total contrast of our image in a much more better manner. So now, since I have told you theoretically, I will have to show you practically
that thing as well, right? So that is what I have already done here. I have just plotted the histogram for the histogram equalized image as well. And if you see that, now you are able to see the concentrated histogram whatever we had is basically totally expanded. Yes, we have the number of pixels in the gray region, but along with that the few set of pixels have been shifted to the darker region and few set of pixels have been shifted to the brighter region as well, right? Which basically helps us to improve the quality of the image in a very simple fashion. Along with that, now if you want to see where this basically this shifting is happening in what region, so we can have this something called as, we can take the extraction of something called as transformation curve. So in order to do that, what we have to do, so along with the standard inbuilt output, which is basically the histogram equalized image, we can also take one more variable which is basically called as t, which is optional variable. If you really want the transformation curve, then only you have to take this second variable. Again, this t can be any other user defined variable according to your requirement, but in my case, to give you more meaningful, so I'm just giving this variable name t. The reason why is this t will have the transformation curve for our given histogram equalization. So once I execute for the same histogram equalization function histeq here, we'll be getting the histogram equalized image in the variable j. So which is again the same image if I do IM show for the variable j, which is the same resultant image here, right? But along with that, if I just normalize this image, I'm just taking that t variable and I'm just normalizing that to 0 to 1 domain. And if I just do that, you'll be able to see that we have transformation for the histogram equalization is happening in only a small window of pixels. Not all the pixels are getting transformed. So only those pixels which are existing in this particular region, only those pixels are basically transformed. Remaining all the pixels are kept as it is. No changes have been done in the remaining pixels. So that is how you can also easily understand how this basically transformation is happening. So we have multiple other images that are available to us. For example, you can apply this to one more inbuilt image available to us called as tire.tif, and you can check out how basically this histogram equalization works. But to understand it in a very simple fashion, it basically expands your concentrated histogram so that you will have much more better contrast in the resultant image in a very simple fashion. So that is basically how the histogram equalization technique works. So now we have one more modified format of histogram equalization technique, which is basically called as contrast limited adaptive histogram equalization, or in short form we can also call it as adaptive histogram equalization as well. So this adaptive histogram equalization is a technique where if you don't want the expansion of your whole histogram full blown like this, right? This is a full blown expansion, but I don't want this kind of expansion to happen full blown like this. I want it to happen only where it is necessary. So we can have adaptive histogram equalization to achieve that particular result. So this is a particular technique where in the adaptive histogram equalization, it will manually check, so between the consecutive pixels, whether I can find sufficient contrast difference. If yes, then histogram equalization will not take for that particular given pixel. If for consecutive pixels there are no significant contrast difference, then automatically the histogram equalization will take place for those range of pixels. So that is the adaptive technique we have available. So we have, again, for this no need to write a separate algorithm. We have the inbuilt algorithm available to us as well. So if you want to deeply understand what is this adaptive histogram equalization, what are the input variables, what are the output variables this function can take, we have the total documentation available in this particular hyperlink. So you can go through that at a later stage. So in my case, so in a very simple fashion, I'm taking the same image here to show you the difference between the normal histogram equalization and the adaptive histogram equalization. So again, we have the same histogram result available to us. And in our case, instead of doing the normal histogram equalization, I'll be doing adaptive histogram equalization. Just as simple as that. And once we do the adaptive histogram equalization, and if I display the result here, now you will be able to see. So this is not a full-blown whitewashed image which were available to us previously. Yep, this image is having much more better contrast compared to original image. But even though it is not doing the expansion of your histogram limitlessly, it is doing the histogram equalization only in certain regions, right? So that is what the histogram equalization will do. In order to understand that, we can plot the histogram for this resultant image as well. And now you will be able to see the expansion is happening only for a limited range only, right? It is not doing full-blown expansion completely. So it is able to find out whatever it is able to find out up to what extent the expansion needs to happen for this, so that I can have a better contrast information. And based on that, it is doing the expansion in a simple fashion. So compared to the original histogram, it is much more expanded histogram we have, but still the contrast expansion is happening only up to a certain limit. So that is what the difference between the normal histogram equalization and the adaptive histogram equalization is. Now, if you want to do histogram equalization for a simple grayscale image, we are able to do like this, right? But what if I want to do histogram equalization for a regular image? For most of our regular image, it will be a 3-channel RGB image, right? So how I can do that? So for example, I have an inbuilt image like this called test2.jpg. So this is the image I'm taking here for our workflow. So if I want to do histogram equalization for this, the reason why I'm taking histogram equalization for this is you'll be able to see there are some regions in this image, especially in the background. So I'm not able to see the whole background image in a much more better fashion. What is basically like here, I'm able to see there is some small window, there is some lighting, but other than that, what is basically existing here? And I'm also able to, there are few set of trees here and there, but other than that, I'm not able to see what is exactly this region is all about. So I just want to apply adaptive histogram equalization to this image so that we can easily able to improve the quality of this image in a much more better fashion. So in order to do that, so the first thing we have to do is we have to basically convert this RGB image to HSV image format. So in order to do that, we have this inbuilt function RGB to HSV. The reason why we are converting this to HSV image is that the V channel in our HSV image format is basically the grayscale intensity. So basically all this histogram equalization, whatever we are applying, we have to apply that to the intensity of our image, which is basically the grayscale values. So that will be available in the V channel of our HSV image. That is the reason why we are choosing the HSV image as the resultant image. So once we do that, so the third channel will be automatically the intensity channel, which will be our HSV image format. And once we do that, so once we will be able to extract that, we can easily apply the adaptive histogram equalization to that. And whatever the resultant pixels that are available, I'll be storing back to the same third channel as well. So that is what I'm basically doing. I'm storing it as it is in the original image. And once we do that, if required, we can also convert that HSV image back to the RGB image, which was our original image format. And now if I show the histogram equalized image here, Now you will be able to see, we are able to see the background of that building in a much more better fashion, and we are also able to see the shadow of that particular person in a much more better fashion. So that is what this adaptive histogram equalization is basically doing. It is trying to improve the pixels where we don't have sufficient contrast difference, and it is creating those contrast difference so that you will be able to differentiate different regions within the image, the foreground, the background, in a much more better fashion. So that is what the idea behind histogram equalization is all about. It is basically one of the image enhancement techniques which are available, and in a very simple fashion to understand, if you have seen the histograms, right? So it will basically expand our histogram in the darker pixel region and the and the brighter pixel region wherever it is necessary, so that we'll be able to differentiate different regions within the image in a much more better fashion. So this is one of the pre-processing techniques that are available. So image image enhancement techniques are the first step that we'll be doing before we do any other techniques as a part of application implementation. So now, having said that, so let us go a little bit further. Now we will be moving towards the thresholding concept. So basically, what do you mean by thresholding? To understand that, so basically thresholding is a concept which helps us to differentiate the foreground and the background in our pixel in a very simple fashion. So in thresholding technique, so we'll be assigning binary values for our complete image. So in our case, if the foreground is very important for us, then we will assign value 1 to that foreground pixels, and for all the remaining background pixels, automatically we will try to assign pixel 0 for that. In any given case, if the condition is vice versa, if foreground image is not so important for you, if the background image is important for you, then you can also assign the opposite as well, where you can assign value 0 to the foreground object pixels, and you can assign value 1 to the background images as well. So depending on your particular application requirement, you can choose these pixel values. So what this basically that is basically the idea behind thresholding technique. So basically thresholding is basically a process in which we will choose a particular threshold level. Based on that particular level, we will be assigning this pixel values 0 and 1 to all the resultant pixel values. That is what the idea behind this is. Now what do you mean by this thresholding level? So it is basically simple. So in any given normal image, the standard data format will be unsigned integer 8-bit, right? The intensity values will be 0 to 255. So between that, we can choose any particular value to be chosen as thresholding value. So in order to understand that, so I had taken cameraman image and I had chosen different thresholding levels, and I had done the thresholding function to be done. So in our case, to show you that, so at the first case, I had chosen threshold value as the 0. That was the thresholding level I had chosen, and I did the thresholding operation for that cameraman image, and you will be able to see, since the thresholded image I had chosen as 0, I had got the resultant image to be completely totally null. None of the pixels had been selected as the valid pixel. Every pixel, since it was more than 0, every pixel was automatically deselected, and we had a complete blank image totally available. In the next case, I increased the threshold to 10, and now we were able to see few set of pixels were considered for our output, and you are able to see the object of our interest in a very simple fashion. And I increased the threshold to 25. I was able to get much more better pixel representation now for our cameraman, and I increased the threshold level to 50. I got much more better representation, but still there were few set of white pixels here and there within the coat of that cameraman, and I increased the threshold to 75. At this particular level, I was having much more thresholded result to be available compared to all the remaining thresholding levels. So this is how you can easily use different thresholding levels, and you can easily achieve the thresholding information. I have this foreground information only to be available, and we have all the remaining pixels to be available as white. So that is what the application is. But still I continued the thresholding since we have the thresholding level till 255. Next I went further and I did for level 100. Then I increased the level to 125. Then I kept on increasing till the level 255. So at the level 255 I got the total opposite image which we had at the beginning. Instead of white pixels, we got to all the pixel to be thresholded as black pixels. So that is how basically the thresholding basically works. So at the end of thresholding, all the white pixels will be assigned with the value 0, and all the black pixels will be assigned with the value 1. As simple as that. So whatever the region of interest you are having, so all those pixels will be represented with color black. So the best thresholding level we got at the most is the thresholding value of 75. So let us see how I did this. What is the program involved here to achieve this particular application in a very simple fashion. So let me quickly move towards this particular script, and let us quickly understand how to achieve this thresholding in a very simple fashion. So in order to do this thresholding, so again I'm choosing the same input image, which is our cameraman, and I'm storing this variable a, and I'm just displaying to just verify whether I have loaded the proper image or not for my operation. As simple as that. Now once we do that, now we have this inbuilt function available called as gray thresh. So gray thresh is a function which helps us to do the thresholding in a very simple fashion. So what this gray thresh will do? Gray thresh is a function which helps us to choose the optimized thresholding level for our given image. So we can manually, if you want to manually do the image, image thresholding, we have to use this function called as binarize, and we have to manually set the thresholding level by ourselves. But if I want the image processing algorithm to choose the best possible optimal thresholding level which can be utilized for our thresholding operation, we can automatically do that. That is the first step I have done here. So we are using this particular algorithm called as Otsu's thresholding algorithm. So this gray thresh basically utilizes that Otsu's thresholding algorithm, and it will basically compute the optimum thresholding level for any given grayscale image we are just applying here. For our given image, cameraman image here, since the input image was A, it is computing the Otsu's level to be around 0.345 approximately. So I'm taking that Otsu's level for our thresholding application, and I'm passing that. This is the actual function to basically produce the thresholded image, which is basically binarize. So this function basically helps you to binarize your image. Instead of taking standard pixel values, it will binarize your image to 0 and 1. So if you want to randomly binarize that, you can directly there is no need to apply any thresholding level. But if you want to binarize with a particular thresholding level, so you have to apply that thresholding level value. So in our case, we are just applying that the Otsu's level computed value as the thresholding level. And once we do that, and if I just display the resultant image which is available after thresholding, so you'll be able to see we have the resultant image which is available, which is almost similar and matching with our 75% level thresholding, right? Not exactly matching, but almost matching to the same level. So the same background image of this particular building with this particular pillars and this cameraman head and the camera tripod, everything is almost similar to this particular resultant image we have got. at the 75% threshold level. So that is how the Otsu's algorithm works. It will compute the optimum thresholding level for our given foreground object, and it will compute the the thresholded value by itself. But if you have your own custom algorithm which will automatically compute that, you can also apply that particular algorithm programmatically, and you can also apply that as a thresholding level to get your own new set of result as well. Now what if you want to apply custom thresholding levels, like the way in which I had shown you in the PPT, right? How I can do that? It is pretty much simple. So we can easily do that. So we have to use IM binarize, pass the image for which the thresholding has to be done, and just pass the thresholding level. If the thresholding level is 0, then the value will be basically the the double value of that given thresholding level, which is basically we can apply that by dividing that by the maximum value. So 0 by 255 if I do, then I'm basically telling that for this the thresholding level is 0. So similarly I can keep on changing the thresholding level. So I have done here, so thresholding level of 10. So this was the, instead of to complete white pixel, we got few set of pixels as the foreground image, and if for the level of 25 we got this, for the level of 50 we got this particular result, and for the resultant of 75, so we got almost similar resultant pixels which we were able to achieve for the Otsu's optimum thresholded. Just even though here not exactly the same level of output, but comparatively the similar kind of result we were able to get here. So what I am basically able to show you here is that you can also do algorithm based approach for doing your thresholding algorithm for your thresholding application, or even if you want to do manual thresholding for any custom level of thresholding you want to apply, we can do that. That particular flexibility is available to us. So that is what I want to show you with this particular implementation. Now where this particular thresholding function is applicable to us, so let's just quickly discuss that as well. So now before we go to that particular discussion where this thresholding function is applicable, I just want to have a quick discussion that even this thresholding is not limited to the grayscale images only. We can also apply this thresholding to color images as well. So if you want to do that, there is no need to write any program for that. We have an inbuilt application that is available to automate that color thresholding process, which is basically called as color thresholder. So let me quickly show you. I hope I have a color image in my current folder. Let me just quickly view that. If that is available, then I can show you that particular workflow right now. If not, then I can show you that in the next particular session as well. That is not a huge task. Let me just check. Well, yeah, I have this test2.jpg, right? Since that is the case, I can show you the working of color thresholder very quickly. So in order to access the inbuilt apps, so we have to go to this home tab. Sorry, it's not in the home tab. Sorry, we have to go to this apps tab, and we have to click on this drop down menu, and we have to focus on the section image processing and computer vision. In that we have this particular, we'll be having this particular app called as color threshold. So we have to just open that color thresholder app in order to do thresholding for given color image. And this is how basically the app looks like. We were able to see in the PPT screen, right? So the first thing we have to do is we have to load our particular file. So since it is available as an external file, I'll be choosing load image from the file. So it will show all the existing images in our given folder. So I have two set of color images. I can choose any one particular image. In my case, let me choose this test2 itself. So once I choose that, now what it will show is it will show a display of that image, and also it will give me option to choose the color color space for our option. So depending on your requirement, you can seek through the complete color space window, and depending on your requirement, you can choose any suitable color window which is helpful for you to do the thresholding. So in my case, I'm feeling that if I want to threshold if I want to keep only the brighter pixels here, so I'm able to see I have this lab color space which is having much more better differentiation from brighter pixels compared to the darker pixels here, right? So I'll be choosing this for the thresholding application. Let us see how the workflow looks like. So in my case, I want to keep only the brighter pixels which are available in my complete pixel point cloud, right? So if that is the case, then what I need to do is I need to just select this polygon, and I have to just set a region where only the pixels which I want to keep are valid. So this is a small region where I'm choosing all the bright pixels in my case. So let me go back and complete this polygon here. Yep. So by doing that, you're able to see I have only the bright pixels which are available, the land where we had the sand on top of which that particular human was standing, and his particular jacket which he was wearing, and his particular face. So all those particular pixels were bright, and also the light which was turned on, and also the window where it was having bright light, even those pixels are also getting highlighted. But majorly it is almost taking those bright pixels as much as possible. Now if you want to seek those particular window, and if you want to do particular thresholding, so you can manually choose that. So by seeking this complete threshold, now in this case we are keeping only the dark pixels, we are negating all the bright pixels. In our case, the jacket, where the bright pixels were there, where the light was reflecting on, those pixels have been totally gone. Even the face has been removed, and also the sand where it was totally bright, even those regions have been totally removed, and we have only the dark pixels being available to us. So like this, we can easily do the thresholding depending on our case. If we find this particular color space is not good, we have once again option. We can click on this new color space, and again we can choose different color space depending on our application, and we can go further and we can choose our color space whatever we want in a very simple fashion. So again, here we have the same flexibility available depending on the color space. We have the color space sliders for our case, and along with that we also have the point cloud, wherein which we can threshold our given pixels in a given fashion very easily. So so like this we can easily do the thresholding in a very simple fashion. So this is the color thresholder which is available to you. So all these flexibility are totally available. Once you have the proper thresholding being available to you, you can easily convert that to a binary mask so that you can easily do the thresholding, and you can save that according to your requirement. So if you want to keep only the thresholded image, then you can also convert that image to then you can also convert that image wherever the region which is your foreground, you can invert that, and you can also store that result. Now how you can store these kind of results? So it is very simple. So we have this option called as export. So if you want to automate this application for multiple images, then you can convert this complete whatever we have done in an automated process, you can convert that to a MATLAB function, which helps you to see what is the MATLAB code involved to bring this application into reality. Along with that, if you don't want to convert this into code, if you want only the resultant images to be available to you, then you can also keep only the image files. So you can only export the images as well. So where in which you will have the option to store binary mask, the versional RGB image, and also the masked RGB image to be available to you. So all these options are available based on your requirement. You can give user defined names in this window, and you can easily store that in your current workspace. Once you click on OK, whatever the file name you have given, so whatever the variable name you have given, all those variables will be created and it will be available in my particular workspace in a very simple fashion. So if I go here, you will be able to see we have the image BW, which is basically the masked image, and also we have the input original image. So and also we have the masked RGB image available. So all these three output are automatically available to me in my current workspace. Since I had not changed any file name, I had kept only the default file name to be available, and all those three input images are automatically available to me. So in our case, we can quickly view those files very quickly. Let me create a new section and let us quickly view those files one by one. First image is the mask BW. Right? And the second image will be this asking which BW you are focusing here. So I'll tell this is the BW. I don't want the inbuilt BW to be taken care. Then once that is done, so the second image we have to view is the versional input image. It is available with the name input image to be available to us. And along with that, we have the final image, which is the masked RGB image, where the thresholding has been done. Let us quickly execute this and let us quickly view what is the output that is available here. Okay, there is a small error. It was not able to identify where this A is. So let me execute this section. This should not be able to produce any further errors. And now this should basically solve that particular error that we were able to produce here. Yep. So now let me just quickly execute that section once again, where we were running that particular file. Okay, I think we had deleted that older file. So let me just quickly store that exported files once again, and let us execute now. Yeah, now I think this should solve the issue. Yep. So now we are able to see. So this is the mask, that is being utilized for doing the thresholding. This is the versional RGB image, which my color thresholder utilized. And by using this mask, so this is the end masking it has been able to do. So like this, you can easily make use of color thresholder. So if you want to, delimit specific colors, and if you want to keep only specific colored pixels in a given colored image, writing your functions will be good, but if you are able to use the color thresholder app, it will be much more easy and flexible. And once you have got the proper result available, so you can easily bring your results to be available as a image file, or even you can also see what is the code involved. So this is how you can easily make use of color thresholder app to achieve that. So now, having said that, so I was also talking about a few set of other pre-processing techniques, right? So in this particular section, we will be quickly talking about the edge detection technique, which is very helpful for us to understand how we can use MATLAB to do this edge detection technique. What is this edge detection technique is all about? how it basically operates in a very simple way. So let us have a quick understanding that here. So when it comes to edge detection, so what you mean by edge detection is it is one of the popular technique which helps us to understand the boundaries of an object. So in any given image, we will be having the region of our interest, right? So in that particular region of interest, if you want to find out the existing boundaries within a particular object of your interest, then we can make use of this edge detection technique to extract those boundary information, and we can easily do that in a very simple way. So how this basically edge detection works? So it is very simple to understand. It basically identifies whether there is any discontinuity in the pixel brightness. So if there is any pixel discontinuity in the pixel brightness, basically this particular technique identifies that there is an existing edge between existing edge in the particular image. So this is basically where this particular edge detection techniques are useful. So you may want to segment a particular region of interest in a given image. Then in that particular technique, edge detection is one of the pre-processing techniques which is helpful for you. Or even if you want to do particular data extraction for any given image for maybe your machine learning technique, even that is where edge detection will also become one of the pre-processing technique which helps you to give suitable data information in a very simple fashion. Now, having said that, let us have a quick understanding, what do you mean by edge detection? What is basically happening in any given edge detection technique? To understand that very easily, so I have taken a simple image where if you see the left end, the color in grayscale intensity starts from dark pixels, from the very dark pixel which is available black, and it is increasing the intensity over a particular rate. Here you are able to see, right? And it is moving towards the bright pixel regions, which is totally towards the region white. So I'm taking this particular image to understand how edge detection basically works. So if I want to do edge detection for this image, so what basically most of the edge detection algorithm will do in the background, basically the first thing it will do is it will first differentiate your given image in a very simple fashion. And once you have a differentiated intensity profile available to you, then it will basically intuitively choose a optimal thresholding level. So as I was talking about, there are various algorithms that are available. One of the popular algorithm it will chooses Otsu's thresholding level. So it will choose the optimal thresholding level that will be available for that given grayscale intensity images. Based on that, it will choose a optimal thresholding value, and it will do the thresholding right away. By doing that, at the end we will be able to do edge detection for a given image. You are able to see we have the region where we have intensity variation from dark to grayscale level. So we have this one edge, and also on the right end we have one more edge where we have intensity variation from gray intensity level to totally bright white pixel intensity level. So even that is one edge we have here. So that is how basically the edge detection basically works in a very simple fashion. So there are various edge detection techniques that are available. So basically all these differentiation and all this thresholding will be automatically taken care by those algorithm. But even if you want to do manually by yourself, so even MATLAB supports you working with the neighborhood operation for your given pixels, and even you can apply those partial differentiation using the inbuilt functions. And also for your particular thresholding level application, you can also use the simple functions like this for x and y direction application to be done. Now along with that, if you want to see the different edge detection operators, so one of the operator that will be available for us is previt operator. So for that, it will basically take these particular values for x and y thresholding, and we have Sobel edge detection operator, where for that same expression we we will take the constant C to be equal to 2. By doing that, we will get the Sobel edge reduction operator to be available. And by doing that, for that same expression, we will get a matrix value like this. So we'll be seeing in terms of execution how the different operator gives us the result. No need to worry, but this is just a simple overview. Along with that, we have one more popular edge reduction algorithm available called as Canny edge reduction operator. So this is pretty much popular because, let me just show you. So how the output will be after to complete operation. So at the end of your candidate edge detection operator, you will be able to see we have the total resultant image available to be available in a very simple fashion like this. So even the smaller intricate variation in the intensity also, it will be able to easily identify that, and you will be able to easily identify those edges in a very simple fashion using Canny edge detection operation. So now, having said that, so let us quickly move towards the code section. We have 5 more minutes. So let us just discuss this particular edge detection implementation. So post which we can take a break. So now, having said that, so I'm using this particular image called as binary img1.jpg, which is the image available in my current folder here. I'll be utilizing this to do the edge detection. So you are able to see the image here. So now if I want to do the edge detection for this, so we can use multiple edge detection operators that are available. So Canny, Sobel, Previt, which you are able to see, are only few set of edge detection operators. There are more than that. If you want to see what are the different edge detection operators which this particular MATLAB function supports, so you can easily go through the documentation for that. So let me quickly show you the documentation at the end once we do this implementation. But let us take the 3 set of operators which we had discussed in the slide as a part of implementation. So how I can do the edge detection? So in order to do edge detection, we have this inbuilt function called as edge, for which we have to pass the grayscale image for which the edge detection has to be done. And then we have to mention what is the method which we are using for the edge detection. That's all. So by doing that, automatically it will be able to do the edge detection, and whatever the end binary value we will get, we can store that in the output variable in a very simple fashion. And we are also displaying all those images at once using this function called as montage. So whenever you have multiple images, more than one, and if you want to display all the images in a sequence fashion, you can use this function montage to simplify that. So in this, you are able to see we have the output for all the 3 operators. The first image is the resultant for Sobel operator. The second image is the result for the resultant image after applying edge detection with using Previt operator. And the final image which you are having at the bottom here is the resultant image after applying edge detection with Canny edge detection operator. So now you are able to see comparatively, if you compare and identify which is the best edge detection that is available to us, we can easily identify that if the given result is only the outer region of our coin, which is the circular edge detection, then the Sobel edge detection operator or the Previt edge detection operator has done almost pretty much a better result. We have to do simple pre-processing. We have to do some morphological operation where we have to remove this unwanted in white pixel between the circular region. And by doing that, we'll be able to get the end result operator much more easily using either Sobel or Previt, right? But even those, embossing within the coin, even if that edge detection is also important, in that case, Canny edge detector is giving us much more better result compared to Previt and Sobel operator, right? So that is how you have the operators. All the operators are available to you. So using simple function edge, you can get the end result right away, and based on your end result, you can choose whichever the output is suitable for you, and you can easily bring the best suited results right away. So I was talking about that only Sobel, Prewitt, Canny are not the only edge detection algorithms available, right? So what are the different edge detection algorithms available? So in order to understand that, so whenever you are coming across any new functions in the MATLAB like this, so no need to think that it is a black box, it is doing some operation in the background without any idea. So no. So you can go through the documentation and you can easily understand what that function is basically doing. So in our case, we have some unwanted warnings which was occurred due to some the error which we had then that had occurred due to the non-execution of the older section. But now, since that execution has cleared out, we can clear the command window, and in the command window you need to type the keyword doc, and you have to just copy paste the function with which you want to view the documentation of that particular function with. So in my case, if you want to see the complete documentation of the edge detection function, which is basically function h, so you can just copy paste that function name after the keyword doc, give a space, copy paste that function name and just hit enter. By hitting enter, automatically MATLAB will be able to understand that, okay, I need to show the documentation of this function edge. As simple as that. And now you will be able to see we have the complete MATLAB documentation for this function. So what is this function edge? It is basically the function which can be used for finding the edges in a grayscale image. And what are the different syntaxes with which you can utilize this function with? So what are the different use cases? So we had used this particular use case, right, where we use the edge and pass the grayscale image and also mention the operator or the method with which we were able to do the edge detection with. But there are also other options that are available. You can choose the if you want to choose the thresholding level manually by you can choose yourself, or even if you want to choose the edge detection direction also, you can choose that. So all those options are available for you. So there are multiple inbuilt functions this function basically takes. So now if you want to understand that, so after this syntax cases, you have description function, where for each use case here, it will give you complete explanation what this particular syntax use case will do the operation with. Along with that, it will show you some examples like this, where you can see the implementation of that particular function with a simple example use case. After that, the important section comes here, where it will show you all those list of input arguments this function will take, and the complete description of those input arguments, what are the standard data type it will take, whether it has any default values it will consider. All those operations will be automatically taken into consideration here. You can easily understand. So here you are able to see we have totally for this detection function, we have totally 1, 2, 3, 4, 5, 6, 7 number of edge detection of operators that are available to you. So you have flexibility to use all these 7 different operators, and even the description for all these functions are automatically available to you. So we have options to choose if you want to use the Laplace of Gaussian filter based edge detection technique. You can use this function method as log. By using that, you will be using that particular edge detection method to do the edge detection operation with. So if you want to use the canny edge detection operator, but even though you want to do that canny edge detection operation very quickly, so for high resolution images, canny edge detection operator may take some time to bring the result. So in those cases, you can also use approximated canny edge detection operator, which will basically give you the results of your canny edge detection operation much more faster compared to the actual canny edge detection operation. But again, we have a simple trade-off, that the efficiency of canny edge detection operator is much more better compared to the approximated canny edge detection operation. But in most of the cases, both the operator will be able to give you much more better result. So that is something you have to keep it in mind. So you can go through the documentation and you can choose easily which is the suitable edge detection operator you want to work with. But here you are able to see, if you don't mention the edge detection method, the default operator will be the Sobel edge detection operator. If you want to choose any other operator, you have to manually define yourself. Otherwise, it will by default choose a Sobel edge detection operator, and it will give you the resultant right away. So along with that, even if you want to select the thresholding level manually by yourself, you have this threshold available to you. If you want to choose the thresholding direction, you can do that manually by yourself. And along with that, even you have the output arguments available to you. So you have the automatic binary thresholded output image, and along with that, even if you want to check out, so you had not selected the thresholding value by yourself, you had allowed the algorithm to choose by itself, right? So in that case, if you want to identify what is the thresholding value it had chosen to do the thresholding with, so you can even compute, even you can extract that thresholding output as well. And even along with that, even if you want to see the vertical gradient, even you can extract that output, which is suitable for the most of the functions. But here also it is able to show you that for your vertical gradient, if you have chosen Roberts as the edge detection method, then automatically the gradient output will be 45. So that is as simple as that. So here also you are able to see if you want to even calculate the direction in terms of horizontal gradient, you can also compute that, the edge detection direction. And along with that, here also it is telling that if you have selected the Roberts method, then automatically the output of this horizontal gradient will be the 135 degree. So all these options are automatically available to you. It is not like it is working in its own way. You can easily go through the documentation, and you can easily understand for any given function why that particular output will be available to you. And even if you want to achieve a specific output, what are the necessary input function arguments that are available, in that what are the specific fine tuning you need to do in order to get that particular output in your case. So always I recommend you to go through the documentation thoroughly, and you'll be able to easily understand how you can achieve your particular output with the help of that inbuilt functions in a very simple way. So we have almost come to the end of this particular session right now. So we have morphological operations pending, and also one application implementation. So we'll be talking about that in the upcoming session, where we will be also talking about machine learning techniques. So we'll be continuing that session post the lunch. So now we can take a break for this particular session right now.
Thank you, sir. Thank you for your wonderful session. There is a small announcement for the participants. So now inaugural function is going on. So you can join through the link provided in the WhatsApp group. And I request all the participants to join the third session at 2 p.m. Thank you so much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Okay, sir. Thank you, sir.
Thank you, sir.